Okay, good morning, everyone.
Yes, good morning, everyone. It is 8:30. However, we see a number of people still logging in, so we are going to wait a few minutes here to allow people to join.
Good morning from a snow-packed Utah.
Oh, good morning, Professor Pantelides.
15 inches yesterday, Professor
Wow.
Conte.
Well, this is still low compared to Switzerland,
I agree.
but it's still it must be beautiful this morning.
Yes. Here.
We have ice on the ground, Chris. Really
Gosh, I do
thin
not see
layer.
any cameras.
Do you see anything?
Yeah.
You don't see?
Yeah, we can see it.
Oh yeah.
Kurosh, how can I see cameras?
You're presenting, so it's hiding.
Oh, I
the
see.
cameras.
I see.
Yeah, you're
Okay.
It looks good, Chris. We have
Yeah.
a thin layer of ice. Thin layer in San Diego.
That's less than Switzerland.
Yeah, where I live in San Diego, there is maybe 1 inch, 1.5 inches every 10 years on the average.
Yeah.
We had it twice since I'm here.
Well, 1.5 inches, we don't even go out to shovel it.
Yeah. Is it powder type snow or heavy?
It's yesterday was heavy. It's usually powder because we have the salt lake, and the salt reduces the specific weight of the snow. That's why we have the best snow on earth.
Mm-hmm.
It's powder. It's puffy. It's really fluffy.
Yeah, no, that's great.
So you guys are welcome to come here and ski.
I think we'll wait till next summer, Chris.
Summer? Okay.
Kurosh, how are we doing?
Event, I know you're
Still
working.
people,
people are still signing in.
Signing
Maybe
in.
give them another minute or two if that's okay. And we can begin.
Sure.
Just to make sure everybody joins.
I see there are some chat questions. No, not yet. Okay. In the meantime, have a nice coffee. Hope you have a nice coffee and a nice piece of cake.
Oh, that cake does look good.
You're accounting for the 9-hour difference right now in Switzerland with that piece of cake. Otherwise I would question your breakfast choice, Joel.
Yes, it's more like a dessert, huh?
It's a sweet tooth, yeah.
All right. Well, so we don't waste too much time. Why don't we
Yeah,
just
I
begin?
think
and
let's
people can
get started. So good morning, good afternoon, even good evening, I think, for some of you. My name is Joel Conte. I'm the PI of the NHERI experimental facility at the University of California at San Diego. I'd like to welcome you to our 8th user researcher training workshop. It's again, due to COVID, virtual. We hope that the next one will be in person or at least hybrid. And I would like to, let me see here. I would like to go through some general housekeeping items before we before we start. So all the presentations, PDF versions, and the items that are listed above there are available from this drive. I think Kurosh will also put this drive link on the chat box. For those of you who requested PhD credit certificates, please contact Dr. Kurosh Lotfizadeh. You have his email here. And if you have technical difficulties during the workshop, please contact him as well. So I would like to go through the agenda of the workshop. So this is day one that will focus on facility capabilities, past project, best practices, and for proposal preparation. So we have now the introduction, and then I will present facility description and capabilities. And then Professor Lely van der Nijnde will talk about the education and community outreach aspect of our facility. Then we will have Design Safe, which is a big part of the NHERI network. Presentation by Dr. Tim Cockerill, who is the Deputy Project Director at the Texas Advanced Computing Center. And Professor Gilberto Mosqueda will talk about design safe tools and capabilities that are very important for researchers. Then we will have question and answers and open discussion, then a break. Then Professor Tara Hutchinson will talk about preparing an NSF proposal utilizing NHERI at UC San Diego. We will have a virtual walkthrough of the facility that we prepared so that you have to give you a little bit the feeling of being in person here. We are still finalizing, as I will explain, the upgrade of the facility to 6 degrees of freedom. Then Professor Jose Restrepo will talk about structural system, list of open issues, and scope of problem and example use of the facility to address scientific needs. We'll have again some question and answers and open discussion, and then some brief concluding remarks at 12:30. This will conclude the first day, and then we will go to the second day here that will focus on new capabilities, equipment, future project, and payload opportunities. There will be some welcome and going through the schedule again, and Professor Tara Hutchinson and Professor Chris Pantelides from the University of Utah will present the modular test bed building that has just been built for the first time a few weeks ago, and that will be available for people writing research proposal and doing research at our facility. Then Professor Shailing Pei, Professor Kerry Ryan, and Professor Andre Barbosa will present the first big project that will come after the facility reopens. It will start at the end of March. The big project Tallwood, a full-scale 10-story building. And then we will have a break. Then Dr. Gianluca Cusatis from the National Science Foundation will have a presentation on NSF NHERI facilities and research programs. For those of you who are planning to write proposal, I'm sure you will have a lot of interesting questions for him. And then we will have a presentation by Dr. Elena Kalinina from Sandia National Laboratories jointly with Mr. Nicholas Klimishin from the Pacific Northwest National Laboratory. They will talk about an upcoming project on spent dry storage system for spent nuclear fuel. And then we will have Dr. Kurosh Lotfizadeh talking about IT resources, cybersecurity and instrumentation and data acquisition, and some concluding remarks. Now, during the presentation, if you have questions, please type your question on the chat box or raise your digital hand, and Dr. and Kurosh will allow you to unmute yourself and speak. So the workshop objectives, right? So we want to show you the new capabilities of the upgraded shake table here. We used to call it LH Post, Large High Performance Outdoor Shake Table. Now, to distinguish it from the 1 degree of freedom version that existed for 15 years, we're going to call the new one LH Post 6. We want to also talk about the resources and equipment available at our site for researchers. We want to go through, help you exploring opportunities to use the LH Post 6 for various types of NSF research proposal, and provide information and our experience and best practices for competitive proposal preparation. We want also to talk about grand challenge research needs to advance the science, technology, and practice in earthquake disaster mitigation and prevention, and to improve the seismic design code and standards, and brainstorm on example use of the facility to solve some of these grand challenges, and also promote collaborative team research, since the specimens that are tested here are very significant. Very often it's beneficial to have a group of researchers forming a team to tackle a very large problem. So let me introduce the NHERI at UC San Diego team. So I'm the PI, and there are 4 co-PIs. Lely van der Nijnde is co-PI in charge of education and outreach. Gilberto Mosqueda is co-PI in charge of site performance. Benson Xing is in charge of site operation, and Tara Hutchinson is responsible for user services. Then we have Professor Jose Restrepo and Enrique Luco, who are senior personnel. Jose was the first PI of, at the time it was NICE at UCSD, and then Enrique Luco was the second one, and I'm now the third one. We have Dr. Kurosh Lotfizadeh, who is site operation manager. He has been with us now for over a year, 2 years soon. Then we have Melissa Zhang, financial manager. This aspect is also very important. She's very helpful to the site, and if you come to the site and do research, you will have to open some accounts and so on, and you will deal with her. We have Abdullah Hamid, development engineer, who joined us a few months ago. He was in the Power Lab for a number of years, then was in worked in the Ferguson Lab in the University of Texas at Austin, and joined us back a few months ago. And then we have Robert Beckley, IT manager, Alex Sherman, development technician and safety officer, and Jeremy Fischer, development technician. And if you work here, you will see them very often and need to talk to them very often. So now the outline of my presentation on the, let me see here, yeah, on the NHERI at UC San Diego. So I will give you an overview of the Engelkerk Structural Engineering Center, which is the location of the shake table. Talk about the large high performance outdoor shake table. This time I modified my presentation I'm going to give you a blend of the 1 degree of freedom and the 6 degree of freedom, so that you can appreciate better the transformation from the 1 degree of freedom to the 6 degree of freedom. And then give you a select set of shake table tests performed on the NHERI at UC San Diego shake table. Talk about the 6 degree of freedom upgrade. These topics will be intertwined a little bit. And then new research opportunities made possible by the LH Post 6. So let's look at the Engelkerk Structural Engineering Center. abbreviation ESSEC. It is located about 10 miles, almost straight east from the main campus. And for those of you who would fly in, it's about 26 kilometers from San Diego International Airport. If you're not stuck in traffic, it's I would say 15, 20-minute drive from the airport. This is a bird's eye view of the site. You see a number of important things here. There is on the left a soil structure interaction facility. It's not directly part of the NHERI experimental facility, but it's available to NHERI researchers on a recharge basis. There is basically a very large reaction wall here, reaction mass, with a natural soil pit 21 feet deep on each side. Then you see here in yellow the shake table. And we were testing at the time some electrical poles with transmission line. You see some safety towers here. You see the yellow line give the outside perimeter of the reaction mass, and the red line is the inside. So reaction mass is between the red and the yellow line. You see the hydraulic power system building that has all the hydraulic power needed to operate the shake table. And there is also a unique blast impact test facility that makes use of the same pump as the one needed for the shake table. Here you see two pictures just to illustrate the use of the soil foundation structure interaction facility. You can see on the left a bridge abutment that was tested a number of years ago. And then on the right, some piles in riprap material subjected to cyclic testing. Now the site is accredited through the International Accreditation Service. It means that in over 80 countries around the world, the data produced at the site is accepted with no question asked. We suspended, you can see the date here, we suspended the accreditation during the upgrade. The upgrade started in 2019, October 1st, and we are now in the acceptance test. We'll then have to do the characterization test, and we'll reopen at the end of February if everything goes well. So now let's talk about the large high performance outdoor shake table. So first, the vision for our site is rooted on three critical needs to advance the science, technology, and practice in earthquake engineering. There is a need for further develop the fundamental knowledge to better understand the system level behavior of building critical facilities, bridges, geostructures during earthquake, all the way from the initiation of damage to the onset of collapse. And then experimental data at the system level is still very much needed. This data is crucial to guide the development of model and calibrate them, validate them, and this model being what we like to call high fidelity physics-based computational model that will allow us to progressively shift our current reliance on physical testing to model-based simulation for design and assessment of civil structures. And then large-scale or full-scale shake table testing are the ultimate test, or provide the ultimate level of validation for new concept, new component system, earthquake protective system, new seismic retrofit methods, and so on to protect the civil infrastructure against earthquakes. So here you see a rendering that we have seen many times now, but it's still very useful because it shows you, this is a rendering that was developed actually in 2001 when we first designed the shake table facility. You see the reaction mass here. You see the platen. You see at the, so from 2004 to 2019, for 15 years, It worked as a 1 degree of freedom system, but as you can see in red here, we designed the facility as a 6 degree of freedom shake table, but built it in 2002 to 2004 as a single degree of freedom shake table, where there was only these two longitudinal actuators here. You see the size of the table, 7.6 meters, 12.2 meters, 25 feet by 40 feet. The peak velocity was a key design parameter, 1.8 meter per second. And we have a maximum horizontal force of 680 ton. Now with the upgrade, this goes over 1,000 ton, but as I will mention for a while, we will still limit it to this for safety reason. The vertical payload capacity is 2,000 ton, and we have a very large overturning moment capacity as well. So when we designed it in 2001 to 2002, we wanted to be able to reproduce severe earthquake ground motion, especially the one due to near source ground motions. And because we are in a mild climate here, the lack of height limitation allows testing of very large scale specimen. We are the largest outdoor shake table in the world, the second one overall, the biggest one, as you know, being at the E-Defense in Japan. But over the years, we tested a number of specimens, including this one that you see on the picture here, a number of specimens that could not have been tested at the E-Defense because of the height. As I mentioned, the table was designed in 2001 to 2002, built 2002 to 2004, and commissioned on October 1st, 2004. Since in 15 years of operation, we have had 34 major research and commercial projects at the site. Some of these projects involve the use of several specimens or the reuse of a specimen that was retrofitted a number of times and so on. These specimens, many of them, the majority are building specimen made of reinforced concrete, precast concrete, unreinforced and reinforced masonry, metal building, light steel building, wood frame, cross-laminated timber. And we have non-building type structures like wind turbine that you see here, soil retaining wall, underground structures such as tunnel, and so on, that we will talk a little bit more later. So overall then, what our site provides the engineering community is a way to simulate large near source earthquake ground motion, and now with the upgrade to 6 degree of freedom, including all 6 ground motion components, not just the 3 translational, but also the 3 rotational. We can, test densely instrumented, larger full-scale structural specimen or specimen of geotechnical structures, soil foundation structures, and subject them to very near real-world extreme earthquake conditions. In terms of education, this is a fantastic tool for graduate, undergraduate, K-12 student, media, policymakers, infrastructure owners, insurance, and the general public about natural disasters and the national need to develop effective technologies and policies to prevent these natural hazard events from becoming societal disasters. So here you can see the reaction mass, very large, as you see, 33 meters by almost 20 meters. You can see one of the 2 longitudinal actuators that we used for 15 years. In 2004, when we started, we had 6 pressure balance bearings, very narrow. We needed a big spacer block to fill the gap until we, in 2009, replaced them by real vertical actuators, but that were not dynamically powered. And then we had 2 hold down strut. You see these 2 tubes, nitrogen filled with a piston in the middle, nitrogen at the bottom at 2000 PSI. These 2 tubes applied a very large vertical downward force on the platen. So they pre-stress the platen against the 6 bearings. to provide the overturning moment capacity. Appreciate also the size here from the top of the reaction mass to the very bottom here, 8 meters almost. You see here the platen with the 2 hold down strut, the 2 longitudinal actuators, and you have a view under the platen together with a vertical actuator. So you see at the top of the piston of the vertical actuator, there is a plate here with some channels, radial and circumferential, filled with oil at 3000 PSI, providing a lubricated surface between, you know, this plate and the pink plates here that are called the wear plate or the glider plates under the platen. So the pink plates slide over the top of the vertical actuators. As part of the upgrade, we had to change these 6 pink plates here, make them wider for the new capabilities. And now these longitudinal actuators, each of them is equipped with 2 huge servo valves with a peak flow of 2,500 gallons per minute, each of them a 4-stage servo valve. And you can see here they also have closely coupled accumulators that are here to provide this additional spike in flow that may be needed to reproduce some earthquakes. And these are single-ended actuator, but double acting, so they can push harder than they can pull. And they are equipped with the LVDTs or electronic LVDTs called Temposonic. Right? And now you will see we have 2 of those on each actuator, horizontal and vertical, for the reason that I'll explain a little bit later. So this shows here the 2,500 gallon per minute servo valve. It's a very, very large servo valve, same as the one used for the in Japan for the NHERI table. You see the first stage, second, third, fourth. The first 2 stages represent what is called a pilot valve. It's a Moog pilot valve, and then there is the 3rd and the 4th stage. The spool of the 1st stage of the 4th stage weighs more than 300 kilograms. To give you an idea of the size of it, and it's okay. So now let's look at the vertical actuator here. So we acquired them in 2009, but you see the servo valve that they had was a Mickey Mouse servo valve with a 15 gallon per minute capability, just allowing the vertical actuator to lift the platen a quarter of an inch and to remove it from the pedestal so that it could move, you know, on top of the vertical actuators. The new servo valves that are in place now are 5,000 gallons per minute. So here, so that you still can see, you will see a couple of slides down, I'm going to show the new hydraulic power system. And you will see the difference. We had to remove all this existing one that you can see here. We had for 15 years, 50 bottle of 50 gallon each, 2,500 gallon of accumulator bank with nitrogen at the top. And we with the pump, we pressurize the oil at the bottom of each of these bottles. And when we reproduce an earthquake, we blow down the pressurized oil into the pressure line, the big red line here. You see 12-inch diameter pipe, and then it used to go to each of the 2 longitudinal actuators here. There was no powering of the 6 vertical actuators. And so again, yeah, I mentioned that here we had 2 pumps here. One to provide the pilot flow for all the servo valves, and one to pressurize the accumulator bank. So this is here the motion of the platen. It's old. It's in 2004. You see, it's still a 1 degree of freedom platen. You could see it's open here, the reaction mass. The concrete planks were not in place yet. Here they are in place. They will still be in place again. They are still, the pit is still open at this stage. And you could see here from underneath, you see the top of the hold down strut here. So this is the reaction mass, or we call it the reaction block 2. 2003, we did some forced vibration testing of this block to see what are the natural frequencies of just the reaction mass embedded in the soil. And you see a shaker here. This was a large shaker from Nice at UCLA. We had put one at each end of the reaction mass, and we performed some vibration testing. This shows here the location of all the accelerometers that we used at the time. And this is important. It shows the frequency response function of the reaction mass. So when we applied the shakers, of course, they could apply a force significantly smaller than the force that could later be applied by the actuators. And we verified the force vibration test performed using the shakers. But we repeated some tests with the actuator once they were in place. And in the east-west direction, this frequency response function at the top of the reaction mass here in the horizontal direction, and here, because the mode, there is a mode of vibration that represent a translational and rocking at the same time, right? So the rocking is represented by the vertical displacement at the east or west side of the reaction mass, at the top of the reaction mass, this blue curve. You can see that we have a characteristic frequency somewhere between 11 and 12 hertz, because we have a very large damping, so the characteristic frequency does not correspond exactly to the peak here. We have radiation damping in the range of 30 to 40%. This is one of the reasons why our reaction mass is a light reaction mass. It's 4,500 ton. For a maximum payload of 2,000 ton is very light because we have very stiff soil condition and very large radiation damping. So we could afford to have this characteristic frequency in the operational range of the shake table. And also you can see the deformation. So we are scaled here for the maximum force when we had 1 degree of freedom. In the east-west direction, you can see 1/4 millimeter at the top. And most of this displacement is a rigid body motion of the reaction mass in the soil. The deformation of the wall is a small fraction of this. So then when we realized that, we had no fears about the effect of the deformation of the reaction block on the control, since some of the control use the relative displacement between the reaction mass and the platen, and some use the absolute acceleration measured by the accelerometers. Okay, so now a few words about the MTS controller. So we use the MTS controller model 469D that is used on all large shake table all over the world. It's a linear state variable controller. The 3-state variable are the displacement, velocity, the acceleration. We can specify under, if we want to run the controller under displacement, velocity, or acceleration mode. Most of the time we run it under acceleration mode, which means that the users provide acceleration of the ground acceleration record. And when we perform the OLI, the iterative methods to improve the match between the table motion and the target motion that we want to play, when we do this iterative loop, we compute the error based on the acceleration. That's what it means to be on the acceleration mode. Even when we are in this mode, the control loop is closed under the displacement most of the time, and it's highly recommended to keep only the displacement feedback to close the control loop. Then the TVC has special features to compensate for linear and nonlinear sources of signal distortion that are listed here. So here I'm going to show you from MTS here a block diagram of the controller. I think it's interesting to know it, at least, you know, in general here, if you plan to use our shake table. So if you are the user and you provide a ground acceleration record, you would provide this, and then the reference generator part of the controller would integrate it twice to get the velocity, the displacement, would differentiate it to get the jerk. And then these four signals are each of them is used in a feed forward way in the control loop. So you have feed forward gains here. And then the table record the display through the displacement sensors that are attached to the vertical and horizontal actuator, record the displacement and record the acceleration. We used to have only 2 accelerometers for the 1 degree of freedom table. Now we will have 11. Right, so we record all the accelerometers through the accelerometers, the acceleration, and then there is a feedback generator that makes use of the measurement and also the delta pressure feedback, the force across the actuator piston. And now there is a lot of signal processing in real time to get the best estimate of the true displacement, velocity, acceleration, and force of the system. Right? The best estimate of the true, which are not the same as the measured. The measured are considered noisy. And then, as I told you, the control loop is closed on the displacement. You see the reference displacement is subtracted from the target displacement, and you have the error in displacement. And then there is a feedback gain applied to the error, right, in the control loop. Usually we keep these ones 0. For large shaking table, it's very difficult to, for example, to have acceleration feedback. There are some high frequency that create problem in the control loop, and there are stability problems and difficulty in tuning the controller and so on. However, the capability is there. We could put some non-zero feedback gain here. And then there is the feedback, the force, the delta pressure feedback that is important to damp down the oil column frequencies. I act as electronic damping for the oil column frequencies. We used to have only 1, now we're going to have 6 oil column frequencies because of 6 rigid body mode of the platen. And then at the end of the control loop, you have the control signal that is sent to each of the servo valve. Right, so this control loop that you can hear that was used for 1 degree of freedom is the same control loop for each of the 6 degrees of freedom. Right. So a few words about tuning of the LH post. The process of tuning, what does it mean? It's the process of adjusting the gain that I showed you, the feed forward gain and the feedback gains, and modify the input to the shake table controller until the output that we measure on the table is as close as possible to the signal that you want to reproduce. So there are 3 steps. The first step is the shake table operator is changing manually the feed forward gain and the feedback gain in a very well-defined sequence to bring the shake table transfer function as close to 1 as possible. When the table is driven by a white noise, usually of 5% of 7% G root mean square acceleration. And once this is done, the step 2 is to learn the inverse model of the plant. Because this inverse model is then very important to go for step 3. Right, so using learning of the inverse model of the plant or the inverse transfer function of the plant using what MTS called the adaptive inverse controller, AIC technique. And then in step 3, which is an iterative time history matching techniques, in which at every step, the drive signal to the shake table controller is modified, making use of the inverse transfer function of the shake table. Is modified so that we get a better and better achieved motion of the platen compared to the target motion. And the difference between achieved and target is measured by the root mean square error here in the acceleration. And you can see that in this case, 3, 4, 5, 6, 7, 8, 9. 9 iterations were done, and the 8th one is the best one. So then the drive signal from iteration 7 will be the signal that is then used a few months later when the specimen is built, that will be used to apply the ground motion record on through the table on the specimen. Here you have an example of a 1994 Northridge earthquake record. You can see the target motion in red here, the ground acceleration record, what was achieved by the table in blue. You have a zoom, you can see a very close match. And you also have the match in terms of spectrum, pseudo acceleration spectrum and relative displacement spectrum here. We have a very large shake table. We're very proud of this level of the accuracy of the table in reproducing earthquake signal. It's very difficult to get such accuracy with large shake table. So in terms of instrumentation, we have a very large inventory ready for the users. We have 12 data acquisition nodes with 64 channel leads. So this is over 750 channels. This is a brand new data acquisition system. Dr. Kurosh Lotfizadeh will talk about it tomorrow. It's a 24-bit analog to digital resolution and a very high sampling rate. We typically sample at 200 or 240 or 250 sample per second. We have a lot of, and this is also the new data acquisition system is simultaneous sampling as opposed to multiplexing. We have a large number of accelerometers, over 200 MEMS based. You can see the picture here. We have displacement transducers. You see them here, string potentiometers. Strain gauges are purchased directly by the researcher. We have load jacks, load cells, soil pressure transducers. We have a GPS system with 3 receivers operating at 50 Hertz with an accuracy of between 1 and 2 millimeter. And we have a lot of high-speed camera that are very important, including some that can be mounted on drone. Robert Beckley operate the drone during your test and provide great overall movies showing the right from high in the sky. And then we have a fully configured end-to-end live video streaming production system. We also on social media, YouTube, Facebook, and Twitter. And we have calibration equipment for data acquisition system and sensors because of our accreditation requirements. So now let's talk about some past shake table tests. You see here on this slide a large number of specimens that we tested over the years. I'm going to show you a few short movies about some of them. You see we have large soil box, the laminar soil box here, which allowed to test here an embedded reaction wall in, an embedded sound wall. And the soil was inside the box. And we have here a larger, not laminar, this one, much more rigid soil box with a retaining wall. You see the dirt behind the retaining wall. So let's go now and look at this slide too. Every test that comes to our site, every research team that comes here is using an integrated experimental and analytical approach. Before even starting testing, they already have a detailed finite element model of their specimen that they have calibrated at the level of material and at the structural component level. And now they are waiting for the shake table test to calibrate it at the system level. And once they have calibrated and validated at the system level for the test performed, they use it to perform parametric studies to cover a wide range of design situation for a special class of structures like parking structures here, where they change the number of stories, the number of bays and so on. And all these parametric simulation results are distilled in order to improve the existing seismic design guidelines or produce some new seismic design guidelines, which in turn allow to increase the seismic resiliency of the built environment. So here you can see a test that was a precast concrete garage with precast diaphragm. The diaphragm were very important in this project, as well as the concept of rocking wall. These end walls are post-tension through two pre-stressing bars, rod, to the foundation. You can appreciate also that we compressed the building that was much longer than the width of the platen by the use of outrigger beams and low friction sliders. This will become more difficult now with the 6 degrees of freedom with the vertical motion, but we have some ideas on how to generalize this concept as well. See here the rocking walls. This is another project, a 4-story building, 40% scale. The previous one was also 40% scale. And this is a system where the gravity load resisting system was partially decoupled from the lateral force resisting system. You can see here a friction dampers connecting a slab, the underface of a slab here, to a wall. You see some nice figures here, elevation and the top. Even though we were able to shake in only one direction, the researchers here put a wall. You see this wall here makes it non-symmetric with respect to the east-west direction, therefore generating torsional response in the specimen. You will see a very large torsional response. You can see the use of our GPS. You see GPS antennas here. There is one on the ground as a reference, so everything is, all the displacement are measured relative to the reference station that is on the ground. I'm going to now show you the
Berkeley MCE level in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, running.
A significant amount of torsion. Then on the next movie here, you see the response of the friction damper. Dissipating a very large amount of energy. Here we have a full-scale test of a bridge pier with a very large mass at the top representing the tributary mass of the deck of the bridge for that pier. This was earthquake 8. It has already been subjected to 7 earthquakes. You can see the plastic hinge region has already been exercised quite a bit. This is a Kobe earthquake at the Takatori station at 120% that you will see. You will see the table acceleration here, the acceleration at the center of mass here, and then the moment versus drift ratio and the shear force versus drift ratio, where the moment and the shear force are at the base of the column.
Oh, he didn't touch. He didn't touch.
during this test, this was the first of the earthquake tests in which we had fracture of the longitudinal rebars. So you will see here, this is a GoPro at, at the base, in the plastic hinge region of the pier. You will see a fracture in this longitudinal rebar here, and then followed by this one. It came like a cannon shot. There is so much strain energy released. And then as soon as they fracture, you will see the concrete inside the reinforcement crashing and exploding in blocks. Imploding in blocks, I should say. See, it's a cycle, tension, compression, tension, compression, tension, compression, and now it fractured right here. See that? And now the next one right here. See the block of concrete now that has crashed completely. Okay, we have also large soil boxes. As you can see here, we have a laminar soil box where every frame can move relative to the one below and above through wheels. So of course, now we're going to have one way or another, we're going to have to retrofit it to a two-dimensional shear box with the new capabilities of the shake table. And we have here the large, we call it a stiff soil confinement box. Look at the height, almost 8-meter high. These boxes allow us to investigate the seismic response of soil foundation structural system, and these 1G, large box test can be used jointly with centrifuge test result to validate computational model of soil foundation structure interaction. We can study the performance of bridge abutment, earth retaining walls, like I will show you shortly, and also investigate the soil liquefaction effect by putting a bladder inside the box to contain the water inside the box. Here you can see some of these tests. So you see the large laminar soil box empty here. We are lowering a pile foundation in the middle. You can see here all the soil layers have been applied. You can see the top of the pile, and you can see during the test the deformation profile of the box. Here a ramp was used to incline the soil layers to accentuate the effect of soil liquefaction and lateral soil spreading. Now you're going to see the movie. So you see a few things. You see a little water leak here, so there is water inside. You also see that at this level here, that's where you have the largest shear deformation. It's the layer of soil that was the most vulnerable to liquefaction. And you see here a gradual drift of the pile to the right, as a result of lateral soil spreading due to soil liquefaction. This is here a retaining wall 22 feet tall with a reinforced earth, where the earth is reinforced with some synthetic grid material that you see here. So we had sensors, in the soil. We had sensors on the wall, on the face of the wall, with string potentiometers measuring the displacement. You see the test here. You see the experimental result in terms of displacement here and action here. You see the face of the wall. You see string potentiometers here. And here in white, this is the acceleration of the table, and in red, the acceleration at the top of the wall. So a significant amplification from the bottom to the top of the wall. Here we had some tests about bridge piers on shallow foundation rocking on the soil. This is a very attractive concept in geotechnical earthquake engineering to bring the nonlinearity of a bridge, let's say, not inside the structure, but at the interface of the foundation and the soil. So we had 2 specimens. The large mass representing the tributary mass from the bridge deck. We are inside the large soil box here. All this outrigger mechanism here, this is to prevent the specimen from collapsing and damaging the box. We also have a large staging facility, which is larger than the size of the platen. Instead of being 25 feet by 40, it's 27 feet by 44 feet. It has tie downs every 2 feet. It's 3 feet deep, very, very strong. It's here to increase the throughput of our facility. So if a specimen is less than 100 ton, 100, 150, it could be built here, and then with a large crane could be moved on the platen, or substructures of a large specimen could be built here in advance and then transported to the shake table. Whenever we do testing, we benefit from all sort of medias that bring broadcast the research that is done here. We have a very strong team in the Jacob School, communication and media relations. Tests are reported at the local level, regional, national, international, as you can see here, and so on. So if you were to come here to do some research, our team from the Jacob School could connect you to all these medias. Now let's talk about the upgrade to 6 degrees of freedom. So this picture came from 2001 to 2002, even before we decided to cut the corners. As you notice, our reaction mass now has the corners cut. The only reason for this to save money, budget, to make the budget work was already difficult in 2002 to 2004. So, but we, as I told you, we designed it for 6 degrees of freedom. We already thought about the V-shaped horizontal actuator, bringing a third hold down strut. For 15 years, we had only 2 of them. And then we thought at the time that we would just double the accumulator bank. When we started to do more detailed calculations, this was the biggest surprise. We needed to quadruple it, as you will see it. Therefore, we could not keep the existing one. We had to remove it and come up with a brand new accumulator bank. So this is now the upgraded system. You see the V-shape actuator. You can see that each vertical actuator is equipped with a large servo valve. You see here 5,000 GPM. You can see the pedestal in brown here. We got rid of the 2-1 in the middle. So it's resting on 4 pedestal. And you can see the 3 hold down strut, the top of them here. We added the 3rd one here. You see some impact plate that we will talk about in a few minutes. And then the red pipe is the pressure, the pressure pipe at 3000 PSI, and the blue one is the return pipe. So you see here, each vertical actuator is equipped with a gigantic servo valve, 5,000 GPM 3-way servo valve. You can see here the high pressure fluid entering the servo valve, and you see this flexible hose. It's part of the return. You can see here the 3rd hold down strut. Also some vertical bottles here. They are inline accumulators. And this slide is very important for those who plan to use our shake table. You can see it for the north-south, right? Why do we have the limitation of plus or minus 15 inches when at the top you have 50 inches, and the vertical and the horizontal actuators kinematically they have the capability to move the platen 43 inches. And yaw, right? Yaw it too. So with the yaw, they have the capability to crash the platen, against the reaction mass here. But as you can see, way before that, the platen would unseat. There is 17 inches of seat. As soon as it starts unseating, you have tremendous jet of oil at high pressure, coming out. And you also have 34 inches here, right? So the V-shape actuators have the capability kinematically to unseat the platen and to crash it against the reaction mass here and also here. Because of that, we need to prevent this from happening at all costs. So there are 3 lines of defense. The first one is through some interlocks that are programmed inside the motion controller of the shake table. And every horizontal and vertical actuator has 2 LVDTs, one that is used for controlling the motion of the platen of the shake table, and one that is part of a second control loop, a PLC loop, programmable logic controller loop. In case an overrun is missed by the controller of the shake table, it would be caught by that second line of defense. And if it's not caught by the second line of defense, then the third line of defense is a crash. And we, with MTS Systems Corporation, design a crash protection system that I will show you in a second, which is here, right? We have 4 bumpers, like we call them. Each of them has 42 rods. You see that have been tested in uniaxial configuration. You can see the yielding here. So the idea is to stop a 1,000-ton specimen moving at 1 meter per second, to stop it in 2 inches of displacement. By elongating, the piston would go in. You see the piston here would go in 2 inches. So it will elongate the 42 stainless steel bars up to 2 inches here. And you see all this energy here multiplied by 42 would do the job. You see here the impact plate that must be fixed to the reaction mass that you have seen on the previous figure. So 17 inches minus 2 to stop the specimen. We are left with 15 inches of motion in the north-south direction. And you can see here the finished product with the bumpers at the end of the platen here. So now this is the hydraulic power system that we need. I showed you the one for the 1 degree of freedom table. Look at this one. We had to completely get rid of our accumulator bank that was 2,500 gallon to bring a 10,000 gallon accumulator bank. So nitrogen, right, filled. So here they are rectangle, but there are 75 bottle at 130 gallon each. And then there is a piston at the bottom, and we pressurized, or with 3 pumps, we had to buy 2 new pumps. So with 3 pumps, we pressurized the oil at the bottom of the accumulator bank that occupies about 25% of the total volume of the accumulator bank. So about 2,500 gallon of oil at 5,000 PSI. And when we reproduce earthquake, we blow it down through the pressure line, the red line. You see now we needed 2 at 12-inch diameter, and then in the reaction mass, they do not go down to 8-inch like before. They remain at 12 inches, and we have a complete loop, a ring. We call it the main pressure ring. It has to go and feed each of the 4 horizontal actuators, each of the 6 vertical actuators. And then the blue line is the return. We also need to have transfer pump to pump, and then we have the surge tank, the same as before, which is 5,000 gallon. 5,000 gallon. So we have transfer pump to bring the oil from the surge tank to the reservoir of each pump. We also need to have a provision for blowing down the accumulator, discharging the accumulator. If we have an abort, right, all this pressurized oil needs to be discharged and brought back to the surge tank. You can see here a picture of these. Each of the bodies 21 feet tall, right? This is a catwalk. That's the second story, if you wish. There is a first story below the catwalk. 21 feet deep, 75 bottle. Each of them is equipped with a pressure transducer so we can monitor what's going on with the nitrogen pressure. Also, now that we have a 6 degree of freedom table, right? If we think about the table as a rigid box and each of the actuator oil as an oil column, an oil spring. So then you can create a simple model, right, in structural dynamics with a rigid box and 2 V-shaped springs and then 6 vertical springs. And if you do an eigenanalysis of this, you would find that these eigenvalues, right? These oil column frequencies, 7.4 hertz, which is north-south, 8.9 hertz, the yaw, 9.3 hertz longitudinal, 41 hertz, which is longitudinal with the pitch coupled, and then vertical at 44 and transverse roll at 53. These are the numerically obtained. We are still cross-checking this with what we can measure from the acceptance test. We're in the middle of that now. And of course, as for the 1 degree of freedom LH post, all these resonant peaks in the transfer function of the shake table, right? All these resonant peaks will be damped out or are damped out numerically by the shake table controller using the delta pressure feedback gain and some notch filters if necessary. So we also need, for the upgrade, you see this plank here, trapezoidal, we can reuse it, but the plank that we had here in place of the orange one was too thick now that our actuator can go up and down. So we had to design new one, which are composite planks, steel concrete, that are half done. They will be finished early January. It's the first thing that will be done, and they will be brought down here. Right now, the pit is still completely open, so these planks are not there. But after we bring the planks, we will have a gap all around the platen because the platen can move plus or minus 90 centimeters in the longitudinal direction and plus or minus 15 inches north-south. So this gap will be filled by or closed by these steel cover plates that you see here. Each of them is hinged to the top of the platen and is rolling on a, you can see a very large, very serious caster wheel that is made for high speed and high load. And we have telescopic tubes here that can accommodate all the relative motion. Right? And here there is an animation that one of our PhD students did in MATLAB. You can see here, right, for a vertical motion, how these plates, but now you have to think about motions where there is not only vertical, but horizontal and the roll and the pitch all at the same time. So this was pretty challenging. Professor Restrepo and his son designed this. So here the performance characteristic of the LH post 6, right? So that's what we will be able to have, plus or minus 90 centimeters. So we go from plus or minus 75 centimeters to 89. It's very counterintuitive. You think that you're going to multiply the 75 centimeters by the cosine of the angle. Actually, if you think about it, you divide by the cosine. So we have a mechanical advantage of the V shape. Right? And then horizontal plus or minus 38 centimeters, vertical plus or minus 13 centimeters. The peak velocity was 1.8 meter per second in the longitudinal. It becomes 2.5 meter per second, 2 meter per second in the north-south, and 0.6 meter per second vertical. Then the maximum horizontal force was 6.8 meganewton, 680 ton. It can go to 1060 east-west and 838 north-south. However, until we have a very detailed nonlinear model of the reaction mass that we trust, we will, for safety reason, not exceed the maximum force that we already applied on the reaction mass when it was at 1 degree of freedom. Then you have the peak rotations here. They seem to be small angle, right? 1 degree in the pitch means plus 5 inches on the east-west and minus 5 inches on the east side. For earthquake engineering, ground motion in rotation have not been measured traditionally because it's very difficult, but there is a new field of rotational ground motion seismology that is very, very active. They have now the sensors to measure this, and researchers in elastodynamics have predicted rotation in near field ground motion a few degrees, 1 or 2 is large. And then, okay, so this, and I'm going to show you here a few comparison of target versus achieved. They are very fresh results. Right? We are in the acceptance test right now. Some of these results are a week old or 2 weeks old. So you can see here for the Chi-Chi Taiwan earthquake in the east-west direction. It's one of the components of the Chi-Chi. This is iteration number 1, iteration number 2, and iteration number 3. In the step number 3, remember, of the tuning of the shake table controller, where you iterate on the drive file until you have the best reproduction of the earthquake on the platen. And here you have the pseudo acceleration spectrum. In red is the target, the reference one. And here you have the spectral displacement. In red again is the target one. And then you have iteration 1 in yellow, 2 in orange, 3 in blue. I see that the blue is pretty close to the target. Right? And you see here in 3 iterations, this was achieved. We also like to keep track of what we call the relative root mean square error. Here an R is missing, relative root mean square error of 9% is very, very good. You see that at iteration number 3, the match for this horizontal component is excellent. Then in the Y direction, also excellent. You see some high frequencies here. If you look at them in the frequency domain, they are at 60 or 80 hertz. They are not all of them, but primarily due to the vibration modes of the platen itself, right? And they are very hard. They affect the control. They are very hard to get rid of. However, when we test the structure, a large-scale structural specimen, the specimen would be most likely insensitive to this high frequency component here, unless there are some very stiff non-structural component and system that would be tested. So we are going to, MTS is doing its best to customize the controller, and with the know-how that we will acquire progressively, we probably will improve on that. But still, we are at less than 11% of relative root mean square error. That's excellent. So that's the second horizontal component, and that's the vertical component here. Right. You see, here, more difficult to reproduce, 23%, because our vertical actuator are single acting actuator. Right. They can only push up. They cannot pull down. Right. The pull down is based on removing the oil as fast as possible from the unique chamber. There is only one chamber in the vertical actuator, and relying also on the vertical force applied by the hold down strut. Right, so you see again some of these high frequency contamination here by the mode shapes of vibration of the platen. And then here you are going to see some movies. Again, a week old or so. You can see now exercising the horizontal degree of freedom, the longitudinal. Now you see the lateral. Run. And then the vertical. And now here, I'm going to show you 3 earthquake, triaxial. This is from the Tabas earthquake. It's we had used 6 earthquake, triaxial earthquake record to design the table, the upgrade of the table. So this is one of them. So
run. Tabas, 94%.
So you heard Tabas 94%. 94% is not, doesn't mean that we are reproducing 94% of Tabas. It's a parameter in the iterative methods that in order to reproduce Tabas at full scale, at 100%, we need to set this parameter at 94 because the system, slightly overshoots. But this was Tabas at 100% scale. And now you have here a AC 156. For those of you who are familiar with seismic qualification test, in the code for seismic qualification test, there is this earthquake spectrum compatible earthquake record, which is very, very demanding, AC 156. So let's play it now. Okay, and I'm running out of time, I realize here. Let me show you also the synthetic 6-axial ground motion. This one you will appreciate the 3 rotation and 3 translation. You see the roll, the pitch, the yaw, and the translation. Okay, safety towers. We have 4 new safety towers, 31 feet height each. They can be piled up 2 on top of one another. New research opportunities made possible by the LH-POS-6. I will go a little bit fast so that I just have 4 slides left. We will be able to investigate in full 3D and large and full scale the combined effect of 6 ground motion component, translation and rotational. The rotational have not been investigated much experimentally in the past. Numerically, they have. Some papers show that in some cases, as you can see, a cartoon here where the horizontal, the base horizontal translation here produce drift in the building as much as the base rocking, and this drift could be adding to, they could add to each other, right? And so we'll be able to study all of this, not only for structural system, but geotechnical system, soil foundation structure system, with the effect of soil structure interaction, kinematic and inertial and nonlinear soil behavior, nonlinear structural behavior, and soil liquefaction. Understanding the damping in structural systems still requires quite a bit of research to improve, the model to represent the damping characteristic or energy dissipation properties of structures beyond the hysteretic energy dissipation due to material nonlinearity. Experimental study in dynamic soil structure interaction will be made possible by using the table in conjunction, in combination with the large soil boxes. But we could do some numerical soil structure interaction work and then apply the total foundation motion in terms of translation and rotation applied directly to the shake table. So it would be known in advance, and we would verify the theory of soil structure interactions. Or we could use the large soil boxes under triaxial and 6-axial or 6-axial excitation at the base. And then in terms of seismic safety of unreinforced masonry buildings, a lot of the research has been done with in-plane excitation. If there is out-of-plane excitation and vertical, it could change the result drastically, as numerical simulation has shown. And same thing for reinforced concrete and reinforced masonry. A lot of the design provision are based on experimental results with in-plane forces in the walls. And now including bi-horizontal and vertical excitation could change the picture in some cases significantly. So multi-axial shake table tests are needed to investigate this problem and improve the design codes. For non-structural component and system, there are efforts to develop a reliable, unified design methodology for multi-directional earthquake excitation. So multi-axial earthquake tests at large scale are needed. And for low damage or damage-free, maintenance-free earthquake protective system, some of them are very complex kinematically. It's important to validate them, test them and validate them under six component of ground motion. And then the largest, the first test that will come up will be the 10-story building, cross-laminated timber with rocking walls. This is a 5-university team, and Professor Shailing Pei, Kerry Ryan, and Andre Barbosa will talk about it tomorrow. This will be an exciting presentation. This is a rendering, to scale. You see the difference in height between the hydraulic building and the 10-story building. And you can, most of the information that I showed here is available in this paper that was published earlier this year. And you also have the contact information with each of the PI, co-PI, and the site operation manager if you have additional question and so on. And this completes my presentation. I realize I went over time, but we may have a few minutes for question now, or we'll take them later when we have the question and answers. Kurosh, are there any question in the box or in the chat box?
No, at this point, we don't have any questions in the
Okay.
chat. We do have a block for questions and answers coming up shortly. If you have any questions in the meantime, please feel free to either put them in the chat, the Q&A box, or raise your hand and we can unmute you and you can ask your question.
Very good. So we will go now to Professor Lely van den Einde, who will talk on education and community outreach. So I will give my screen.
I'm not sure. Hold on, here we go. So let me first put I apologize, I'm getting all set up right now. Can you see it?
Yes, yes.
Okay, great. So we'll get back on schedule after my presentation. It won't be very long. I'm Lely van den Einde, and I'm the Director of Education and Community Outreach at the facility. So I wanted to just take the time to talk a little bit about some of the activities that we do and some of our goals in terms of education and community outreach. We have sort of been a little on hiatus just because of the upgrade, but we still continue to participate in a lot of the education and community outreach activities across the network. So I'll talk about that, and I'll also just kind of highlight some ideas if you want to include eco activities in your own proposals and future proposals, just some ideas of what has been done in the past. Okay, so I just want to remind you a little bit about our goals. We have maybe 6 major goals for our site. Obviously, the first is to support technology transfer to practitioners and future engineers. And our major goal is, if you after Joelle's presentation, you saw how amazing some of these tests are and the results that are coming from the tests. It's really how can we get the research results into practice? And so we support this through lots of different events. We're here to support tours of the facility, to enable people outside in the community, whether they're from certain professional societies or other groups, to understand the research capabilities of our site. And we do try to encourage, and I think Dr. Hutchinson will talk a little bit about it, but bringing industry involved into your projects. And so she can talk a little bit about how to do that. We also highlight the research conducted at the university through, in our case, the Jacobs Media Relations Group. And they I'm sure all of you have media relations people at your own institutions, but we do have our own group that's here to help you work with your own institutions to distribute press releases about upcoming tests, and to contact local media outlets. They'll help support a media day. Basically, if there's pitches to local California reporters, if time's permitting, they'll help with video and photo shoots of the tests, and help you kind of organize what you need to do. So we just want to encourage you to understand that we do have this resource available, and they're very helpful to work with your own home institution about how to disseminate and I guess increase the excitement around your tests, since they're all very high profile landmark tests. Again, we also want to focus on demonstrating how the benefits of our research impact the public and as well as critical decision makers. And so this is obviously about how to bring your research results into the codes, how to disseminate the results. And so we, as a facility, we support the work being done through Design Safe, and we can help you with your data and how to get that in there and how to, more broadly disseminate your data. In terms of another goal is to engage students and broaden participation of groups in the area of structural engineering and earthquake engineering, especially focused on underrepresented minorities in STEM. So we do a lot of outreach. We've developed an outreach program from many years ago that brings in 4th through 6th grade students from all over San Diego County, from a lot of diverse schools, and they participate in a Connects design competition. The program is run by our undergraduate students. It's all volunteer based. And we've now leveraged this and call it a seismic outreach ambassador program, because in addition to doing the outreach, we are professionally developing our undergraduate student leaders in terms of how to communicate with all sorts of different people, whether it be teachers or principals, and even working with young kids, how to plan things. So project management skills, and some of the soft skills that we're working with them so that we can develop a group of high achieving engineering student leaders with really strong soft skills. So that's our Seismic Outreach Ambassador Program. And if you're at the facility and you have graduate students who might want to get involved in the outreach, they're welcome to participate. I do want to mention that this has since become part of the EERI School Earthquake Safety Initiative. I don't know if anyone's familiar with that, but we have a classroom education and outreach program. And so some of the curriculum that we've developed for the Connects, as well as for high school curriculum, can now be accomplished through this EERI SESI group. And so I just put the link there in case you want to go get access to the actual curriculum that you can do at your own institutions. So you can bring this type of outreach, which teaches about seismic design to very young students. And so we do encourage you, if you have your own EERI chapter, to look at these resources and maybe get the chapter to engage in these outreach activities. And then finally, we want to provide unique and stimulating experiences for the undergraduates in a research setting. So if you're familiar with the NSF REU program, the NHERI network has its own REU program. We bring 2 to 3 graduate students every summer to our facility to help with the research that's going on in the, at the site. These students often end up going to graduate school and are very, and they come from diverse groups, and they're very interested and active. And unfortunately, because of COVID, we haven't had in-person experiences too much in the last couple of years, but we're hoping this summer that with a 10-story building, we can bring in several students to help with that particular project. So I just wanted to give you some ideas of if you need to include sort of an education and community outreach part in your proposal. In the past, we've developed a lot of educational videos using footage of the experiment. And they're very powerful. They can be made not only for undergraduate or graduate courses. It's really basically bringing research into the classroom. And this just shows an example. Since we don't have time, I'll provide the links. I'll update the slides and can provide the links for you to go check out some of the playlists of some samples that we've developed. I do want to mention that I think these are very useful. We've created quite a few for our own projects here. but they do require a lot of time to do correctly. And so if you are trying to put some create videos as part of your research effort, make sure you put enough resources in there. You need to develop what the educational outcomes would be for the particular video and develop scripts, and make sure ahead of time that you know what you want to accomplish with these videos so that you get the right footage during the experimentation, or if you want to interview some of the researchers, it's great to have this planned ahead of time instead of after the fact. And I'm sure Tara can talk a little bit about her experiences because she's developed quite a few videos, and I'll have one I can show you shortly. These are short videos that we've created ourselves. We post on YouTube. We can make them available. Let's see what other things. Other ideas people have had are developing blind predictions for your particular experiment. So if you know you're going to be doing this landmark test and you want to get graduate students or undergraduate students to participate in a blind prediction competition, basically, then you can develop one of those. So these are just some examples. You can also leverage the curriculum we've used to teach and do the outreach. So if you want to put that into your proposal as well, we're very happy to help provide you some, text or something about the outreach that we do with the 4th and 6th graders. So I think this is going to be a little tricky. Let me stop sharing for a second. And I just want to show you this, one of the, now I'll share the screen again. So this is one of the videos that Tara created. And this one actually, she worked with our UCTV. So we have a TV station that helps develop some really nice video footage. So again, it requires some resources to be able to work with these kinds of groups, but you should think about it in your proposal. And this, I'll just start with a little bit of it, but
UCSD TV.
Let me kind of move it ahead a little bit.
Densely populated regions of North America. Yet less than 100 people perished. While modern engineering did much to minimize the loss of life, lessons are always learned from natural disasters of this magnitude. One of the lessons learned was found in many steel buildings.
So I can actually kind of move ahead and you can see that it brings in practitioners, researchers to talk about the experiment that actually happened on the shake table. So I'm just going to pause it there just because it gave you a gist. Again, I'll give you the link. Let me go back to, can you see? Okay, so yeah, and one of the nice things about that particular video is it wasn't targeting undergraduate or graduate students. It was actually targeting the general public to educate everyone on the importance of and the advances in hospital seismic design and construction practices. So, what's nice is it's really trying to relay the research and practice message to the general public, basically explaining the need for hospital resiliency. So these are great ideas for you to incorporate into your proposals. With that, I just wanted to end it on this particular video. This is that Seismic Outreach Ambassador Program. We don't normally test these structures on the outdoor shake table, but this was right, when we actually had no one on the table, which is very, very rare and won't be the case for the next several years. But we were able to bring, I think it was in a span of 2 days, we brought 300 4th through 6th graders from low-income schools and communities to participate in this Connect project. And I just want to play the video because it's very powerful. How excited and enthusiastic they were with watching whether their structures failed or performed well. So. So again, this is just, how exciting it is to be able to inspire some of these youth. So another option for you, we won't probably be able to do something like this, but it's, similar, developing some kind of outreach event to encourage young kids to get into STEM. So with that, that's all I have. I can open it up to questions or we can wait till another time.
Thank you very much, Lely.
Okay.
So let's see if we have questions. I think not right now.
No questions yet, so we can continue, and then when we reach the Q&A section, we can just open it up for discussion. And
Great.
again,
So,
just to reiterate, people, if you have questions or anything, just put it in the chat or the Q&A, or raise your hand, and we can just unmute you and you can ask your question.
great. So now I would like to introduce Dr. Tim Cockerill, Design Safe Deputy Project Director at the Texas Advanced Computing Center. If you have worked with him or if you have not, he's a fantastic person to work with, very highly responsive and helping very much. So we look forward to hear your talk, Tim, and then we'll be followed by Professor Gilberto Mosqueda, also on the same topic, design safe tools and capabilities.
All right. Thank you very much, Joel. Hello, everyone. Glad to be with you here today. Let me, let's see, this probably, there we go. Try and get some of these things. All right, there we go. Hopefully you're seeing the presentation well. Just a quick note about Design Safe. We are the cyber infrastructure component of the NHERI program, the NHERI collaboration of 12 different awards here. And so what do? We are a web-based platform, so you can access us quite easily just through our website. But the architecture of our infrastructure is such that you can also not only access us that way, but you can access us directly through the command line if you're familiar with that, or if you're have some other advanced computing skills. We have access through APIs, etc. But we provide data management capabilities, and also integrated tools to analyze and work on your data, work with simulation, HPC simulations of your data, things like that. So to that end, on the Design Safe website, if you have not been there yet, the portal, what we call the Design Safe portal, or the interactive portion of the website, is the research workbench. So where you can go and interact with your data, bring data to the site, look at other people's data, and find other data. And also there you'll find our user guides that can help you understand how to use the various features and capabilities within the Design Safe portal. So what all do we have? As I mentioned, we do data management. On the left here, you've got the data depot, and we'll show you a little bit more about that. That's where you can do all kinds of interactions with bringing data to the site, accessing that data, sharing it with other people, and ultimately publishing some of the data if you would like to do that. We also have what we call the workspace, or tools and applications, where you can access numerical simulation capabilities that are sometimes, most of them running on high performance computing systems, other times in virtual machines, all of it at the University of Texas Advanced Computing Center, or TAC, where we have 2 of the largest academic computing systems in the world, and a lot of other specialized high performance computing capabilities, machine learning, all of the various tools and aspects. TAC is 200 staff members, lots of different NSF projects going on. We have a lot of people that can work with you to help you support your research, in addition to our dedicated activities for NHERI and Design Safe. We have the Learning Center, where we give, we and other members of the NHERI program give tutorials, give webinars, provide instruction and support for your activities, for your research. Reach out to us, explore what we have there. Our role is to make your jobs easier to get your work done. And for actual natural hazard events, we have the Recon portal. And in there, you can find different events that have happened or are ongoing. And we collect data set. We collect links to data sets, basically, many of them within Design Safe, but also we will link to other external data as well. So if you want to look for data on a particular hazard, that's a good way to search it out. Data, everything's about data these days, right? So in the data depot, in the Design Safe data depot, we have multiple places for you to work with your data and other data. We have a private space where only you can see that data if you want to have that type of data access. We do not restrict what you bring to us or what type of files you bring to us. Yes, if you're going to do some activity with one of our experimental facilities, and in this particular case, right, UCSD, that data will be available to you in Design Safe. If you have other data that amplifies that activity, or you have other natural hazards projects that you're involved with, any of that data is welcome to be brought to the Design Safe data repository. We have a place called My Projects where you collaborate and share that data with people you select to share it with. It's still a private space, and you can share it with a select set of people. And then ultimately, that's where you work on it to curate and publish it from within My Projects. And then it can become a published, curated data set for other researchers to explore, reuse, hopefully. And you get a digital object identifier, and so you can be cited for other people's use of that data and get credit for that data. If you want to share data more openly to the community that's uncurated, that's fine too. Go ahead. We have a way to do that through what we call community data. And then, as I mentioned, the workspace with the tools and applications. And if you need additional access to high performance computing, we have an allocations process by which you can ask us for additional computing capabilities that maybe aren't available through our web-based tools or the Sim Centers. The NHERI Sim Center develops tools as well, and they're all available through us. If you have other things that you want to do, reach out to us and we can provide you with other access. So supporting your work, again, that's the big part we bring. User-based, we have written support, we have user-based support, we have direct support with, by humans, right? So we have user guides where you can go and read and try and get a better handle on what you're trying to accomplish, whether it be curation and publication, how to use some of the applications. Data transfer, we have a multitude of ways that you can interact. As I mentioned, you can work right through the web browser, do some drag and drop type of things that you might be used to doing in the web. We also integrate with other data, cloud provider data management tools like Dropbox, Google, or Box. And we have other ways for you to move data in with higher end capabilities such as Globus, SFTP clients like CyberDuck. But we can, if you're not sure, reach out to us, and you can read through the user guides, learn what you can. And it's not always easy for everyone. We understand that. That's fine. Reach out to us. We have virtual office hours. And many of the NHERI sites are now doing these as well, I should add, and the link is there for all of the virtual office hours all across NHERI. But we have, for data curation and publication, Dr. Maria Esteva. Oops, I didn't update this. Sorry, Mahyar has moved on. But Dr. Maria Esteva developed all the data models that I'll talk about in a second here. And she is available Tuesdays and Thursdays or by appointment to talk to you about organizing your data, how to use the data curation capabilities and features, and ultimately publishing, and how to prepare a good publication so that other researchers can reuse it. We have now started virtual workspace office hours with 2 new TAC staff members, Joe Van Tassel and Yang Zhang. Both of them are previous users of Design Safe. who have since recently graduated and are now full-time staff members. Joe came from the University of Texas, Wen Yang at UCLA. And so they're very familiar with design safe, with high performance computing, actually machine learning as well, with their projects that they did for their research projects. Take advantage of their time, their expertise, and communicate with them on Tuesdays at 2 o'clock. And they log into the Zoom connection. Again, you can find it at the link there, and you can just chat with them about things. I also wanted to bring this to your attention. Many of you know Joy Poschke, National Science Foundation Program Officer for NHERI. And on December 6th, we had a Publish Your Data event. We had Joy present, and this is just one of her slides that I wanted to share with you. I provided UCSD with all of Joy's slides from that event, so that'll be available to you following this the meeting today. So you'll see she had 4 slides about data management plans and some details there that you'll probably want to see. But she really encourages and values the publication of your data. And so I just wanted to emphasize that as well. Since you will likely be working in the Data Depot, I just want to have a few slides that show you what it looks like. Here's what the interface looks like. You can see some of the private data areas there for what we call my data, my projects that I mentioned before. And then Box, Dropbox, Google integration. You have to log in. A little screen pops up and says give access to your data. And then you can easily move data from Dropbox, Google, and Box into your My Projects, into your My Data. In the public area, then you've got the published projects there. The predecessor project to NHERI was NEAS, which was all earthquake. Now we're multi-hazard, but we have all of the data publications from the previous program under NSF, which was the NEAS, and then the community data. Here I'm showing you my projects, what my projects looks like. And so you can easily see which projects you're a member of. This would be my, actually this is Ellen Rathje's private space. She's the PI of Design Safe. And you can see the projects that, project titles, when it was last modified, who's the PI, so that, and then you can drill into those by clicking on the project title and get in and see the data. I mentioned the data models. Dr. Maria Esteva is a digital archivist here at UT at TAC, and she is an expert in developing these data structures. We worked with you, with the community of experimentalists, people that did high performance computing and simulation. We worked with the field research community, the hybrid simulation community. We developed an ontology, a set of tags and categorization and a flow of how this data can be organized and tagged with meaningful information and structured so that someone else in your field, if you're an experimentalist or if you're a computational scientist, can understand your data by seeing how it's organized and tagged and such. And we implemented that then in software so that your data comes out viewable in the Design Safe infrastructure, and it becomes when we say there's flexibility, and then in that you can still add your own keywords, your own tags. We do have a minimum set of required things that your community has decided should be in there in terms of data organization and naming. But then we still allow some flexibility, and that's where it can get a little bit confusing potentially, right? Because with flexibility comes responsibility, right? As how should I do this? How are other people doing it? And that's why, again, we provide the virtual office hours so that you can just contact us, work with us. We'll work with you. So here's what I mentioned about organizing data. You're going to have a model, right? And that's you're going to have some files that describe what is the design, how is this laid out, where are the sensors located, what types of sensors do I have, events, right? How many unique, in this case, shakings, right? More than likely is what's happening here, right? You're putting ground motions, and that's separate ground motions are going to be separate events. And then you've got some analysis of the output data that you want to include, and probably a written report, right? And so all of this gets organized in a way that other researchers can find it. And if you do multiple experiments with the same model configuration, et cetera, then you can get a separate DOI or separate identifier that people can cite for separate experiments under the same project. And this is what it looks like when it gets published. So it kind of looks like a journal article, right? In some ways, at least the beginnings of one. You've got an abstract title, you've got who's the key people involved in putting this together. Your DOIs are there, right? Keywords. And then the data diagram is basically what we were showing before. How is it laid out? And then you get into each individual experiment. And there's the data diagram that gives someone a visual of how this project is all laid out in terms of the model, the particular sensor information, the events, and then ultimately down below the data collected there at this one in particular, 5,000 hertz during shaking. Also note in the upper right there, we've got download the entire data set. We zip these up, and when you click on that, it'll tell you how large the file is. Will it be the right size that it will fit on your laptop when you do download it? If it's too large, then maybe we need to move it somewhere else. And we, again, look at our user guides or reach out to us and we'll help you with things like where should I move this data? How can I interact with this data? If you need help with that. And data metrics is something new that we've recently added where you can see how many downloads your data has had, or if you're looking at somebody else's data, it might be an indication of value or popularity of somebody's publication, of how many people have downloaded, how many files, and then how many times has it been cited, and things like that. So again, as Joy Poshke said, make your data count. Please use Design Safe. Please publish your data sets, that because you are doing one-of-a-kind experiments often that many other researchers can do, and the National Science Foundation is putting a lot of money and energy into creating these data sets as well, and make them more broadly available for everyone in the community. Get that DOI, it's permanent, even beyond if NSF stops funding this activity, those live on indefinitely, and the data will still remain available. We haven't, what the DOI also does is puts an obligation at our end at TAC to continue to make that data available to you indefinitely. And then cite your data publication in your reference list. This is really important. Journals are getting there. Many of them are allowing this now. Some still haven't quite caught on and say you have to put it in acknowledgements, that kind of thing. But if you can put this in your reference list when you are publishing, it is much easier to find with standard search tools, automated tools, in terms of having your citations being found and counted. And then additionally, things like Jupyter Notebooks. You can separately, if you have Jupyter Notebooks for analyzing the particular data in there, you could separately publish that Jupyter Notebook under perhaps a different type of data model that we have, like maybe the simulation data model, or maybe it's under the other data model. And then you can cross-reference that if you would like. So Again, make your data count. We make it easy for other people who are using your data, or for you, if you're citing someone else's data, we have a little blue box there, a little blue button for the citation. You can just copy and paste out of there, or you can click download citation and you get that proper way of citing available to you. I just wanted to show you one of the UCSD. Gareto published this, and so you can see what a hybrid simulation using UCSD an example is. And so you're welcome to go. You don't even need a design safe user account. We'd love for everyone to get one, but if you don't have one, all of the published data is publicly available. Go look in there, search. There's multiple ways to search and check out the different data capabilities. So just a reminder, user support is key. Just throwing all of this out on the web, that's not just what we do, right? We're here to provide you with multiple ways to get help, to get support, whether that's through the user guides, whether or if you really want direct access to us, you've got it through the Data Depot Curation Office Hours and the Workspace Office Hours, or direct access to other NHERI sites through the office hours. And in addition, I didn't put it in here, but we have everyone that gets a Design Safe account, you get invited to our Slack team for Design Safe, where you can reach out to us. We have dedicated channels for different activities, or you can even direct message me or anyone on our team that you have a question for. So I will stop there. And if anyone has any questions, great. Otherwise.
Yep. Thank you, Tim. There is one question in the audience. I will allow them to unmute so they can go ahead and ask their question. Lewis, you should be able to unmute and go ahead and do so if you still have a question.
Accidental, sorry, Karosh.
Yeah, no problem. All right. So, yep, I think we're good then.
Yeah.
All right. Thank you
very
all.
much, Tim. Very informative presentation. So now we will have Professor Gilberto Mosqueda, who is a co-PI of NHERI at UCSD.
Hi, thanks, Joe. I'm assuming everybody could hear me. Yeah, so I want to follow up on Tim's presentation on Design Safe, and I'm involved with Design Safe at leading one of the use cases, and as well as Joe mentioned, a co-PI on the NHERI site, looking at emphasizing the data as Tim was talking about, and how we can make this data more easy to use and publish later on in the once we're done with the experiments. And this is particularly important, I think, here for tests going on the shake table, because as you know, some of the tests that Joel showed, these are landmark projects. These are huge projects, usually multi-million-dollar projects, and have been some of the most reused in terms of data reuse on Design Safe. I think one of the most reused projects is actually one of the projects that took place, the BNCS project led by Professor Tara Hutchinson. So these are very important projects, very high level, very expensive and landmark projects that usually go on this large shake table. And so it's very important to get the data published in a friendly format so others can use and reuse the data for further analysis. So I just want to start I'll talk about this sample use case project we're developing, but just acknowledge some of the students that have worked on this project. Some have already graduated, and then have a couple of graduate students here from UCSD, and including a student that spent some time in the summer. And also want to acknowledge the project we're working with to try to implement some of these tools, the modular test building project, in which we're working with Professor Tara Hutchinson and some of her students, and Chris Pantelides. And they'll both give a presentation tomorrow on the modular testbed building. So you hear more details on that tomorrow. So building on Tim gave an overview of Design Safe, and one of the tools that I want to focus on is Jupyter, available within the workspace. There's MATLAB, Jupyter, other tools to use. And while most of us are probably familiar with MATLAB, I think it's more predominantly used in our field. There is some incentives to try to go with Jupyter for some of our tools. And one of them is, well, you could access all the data on the cloud, all the data on Data Depot, all the published data, you'd be able to access it directly. You could do something similar with MATLAB, but I think Jupyter provides a much nicer user interface to do some of these analysis. DesignSafe also offers the option to run Jupyter on your computer, or you can run it with an HPC resource if you're doing highly intensive computational tasks. So you run Jupyter from DesignSafe, you then could access essentially any of the data in there. And we're trying to look at using some of these tools from its conception of the design all the way to publication of the data. So including specimen preparation, we can use the My Project space, a private space, to share construction instrumentation drawings with the project team. During the experiments, we could have access to the data, share the data with project team members that, for example, may not be able to attend or be there at the experiments. And additionally, the project team could work on post-experiment analysis and create and publish the data along with some of these viewing tools developed throughout the project, and make it easier for others to also be able to view the data, and again, for reuse. And again, the key goal is to be able to publish your data as required by NSF in particular. So we're looking at how to streamline this whole workflow process with Jupyter Notebooks, and having all this data on the cloud, no need to be passing around data. It's all accessible on DesignSafe. And so for that, if we think about all the data that's developed during an experiment, including from the test preparation, the drawings, instrumentation plan, and then we run the test. There's data coming from various sources, with video, data from displacement sensors, acceleration sensors, many different sources, and then we want to view and process that data again. And so we could do this, store all the data on Data Depot, and then be able to process all this on the cloud using, for example, one of the tools we could use is Jupyter Notebook. And so as part of this use case project, we're developing a template to be able to process data from LH-POST-6. We have the notebooks that we can use to view the data, share data, publish. And again, we could do this all the way to the publication. And then once we publish the data, the user could be able to view that data, view that data as well, using some of the same tools we use. This is, for example, one of the projects on hybrid simulation that was conducted on LH-POST. This is before the upgrade. Some of the data used, and we developed a notebook for this data it could look, once you work on Jupyter Notebook, it looks pretty much like a paper. Once you run the coding, it looks very much like a paper. So it could look something like this. And then as you scroll down, you could get to options where you have options to select, for example, scroll through directories, select the data file that you want to look at, and then run the test and be able to, for example, as Professor Conte mentioned earlier in his presentation, you want to look at the shake table performance, compare displacement feedback, compare response spectra for the test. And you could then also look at the performance of the structure itself. You could plot, again, just simple time histories, or you could process data. For example, we're looking at using some system ID tools for, in this case, applying it to the modular testbed building that, again, you'll hear more about tomorrow. So in that case, we're developing notebooks where you could, for example, calculate, this is using data from past experiments, where we're developing the tools to be able to apply for the testbed structure once the testing is conducted next month. But we could, develop, identify the frequencies, identify the mode shapes of the structure. Right, so these are all tools and plots that will pop up in line with a lot of the written code on the text. So again, it's like having a interactive notebook where you can plot, select what data you want to plot within the analysis. So some of the key advantages is no downloading of data necessary. You can explore all this data on the cloud. You could use these notebooks throughout the development of your project, the analysis of the data for the project. And then once it's ready, you move it from My Projects to Published Data, and then it's out published. These Jupyter notebooks, again, can be used by future users to access the data. If you go to see a typical project now, you'll see a lot of files. It's hard to see what's in those files without downloading them and exploring them, say with MATLAB. But here you could see what's in some of that data before you even download and go into and take a deeper dive into the data. Jupyter has a wide variety of libraries to explore. For example, some of the system ID tools, just like MATLAB does. And then we could, because you don't have to download all the data, we could do comparisons across tests. For example, we could compare how the table performed across different projects for different payloads. We could examine how the structure is as from test to test, as how damage is progressing by, for example, applying damage detection algorithms. And again, all this could be available for you during the project phase, as well as for users after the experiment. I maybe went a little bit too fast, but I know we're somewhat over time, and I want to leave sufficient time for questions if they are any. And I think these are questions for I think any of the past presentations we have seen.
Thank you very much, Gilberto. Kurosh, do we have questions?
We don't have any questions in the chat or the Q&A, but if anybody has a question, now we can have an open discussion. Just raise your hand and we can discuss.
Please do not be shy. You now have heard a number of presentations, so there are no stupid questions. Remember that. We hope to have some interaction with you. Now is a good time. Yeah, there is a question. Yep.
We do have a hand raised. You can go right ahead and unmute yourself and ask your question.
Can you hear me?
Yes.
Hello, professors. This was just a question regarding the rotations of the table. You have the vertical actuators. Are they on a gimbal? How do you? A gimbal mechanism, or the head of the actuator? Can it also tilt, or is it just vertical?
Yeah, thank you for your question.
It must be a tilt, I think.
Yeah, thank you for your question. So the vertical actuators, they can tilt about an axis that is a couple of inches from the base of the piston.
Okay.
So there is a mechanism there, and that's where you can have the couple of degrees, usually 2 degrees. So in other words, right, if the piston can rotate relative to the cylinder of the vertical actuator, then the top plates that is perpendicular to the piston at the top will also rotate by the same amount.
Okay. Thank you.
Yeah, you're welcome.
Yep, if anyone else has any other questions or just wants to talk about something, please raise your hand and we'll allow you to unmute.
Any joke from you, Gilberto?
It can't be cold. I needed some prep time.
Oh, yeah, we have now questions. Very good. So Davide Noe Gorini from Italy and Akash from the Sim Center.
All right, so I'm just gonna go first up. Let's go with Davide. You can go right ahead and unmute.
Hello, Professor. Hello, everyone, and thank you very much for these presentations that are very interesting. And actually, I would have a couple of curiosities that I probably missed before. And the first one, which actually I was wondering which the maximum horizontal acceleration that can be impressed through the shaking table is under dynamic conditions, and another question regarding the sides of the geotechnical box in plan and also in the vertical direction. Thank you very much.
Okay, so maybe I should put my presentation back. Let's see, let me try to show my screen, Kurosh, again. Let's see. Ah, gosh, I lost Okay, so let's go back to the boxes and I will answer your second question, your first question second. So if we go back to the boxes here.
Okay, thank you. Yeah.
Let's see. Here. So you see the laminar soil box, length 6.7 meters, width 3 meters, height 4.7.
Okay. Yes, thank you. Yeah.
And then the other one, you have 10 meter, the length, and then the width, you can play with two different, either you choose 4.6 or 5.8.
Yes, I see.
And the height 7.6.
Okay, thank you.
And then let me see if we go back to your first question, let me show you this table again, right? So in terms of the capability of the actuator, right, we can go in the east-west direction to 10.6 meganewton, which is 1,060 ton. So if I bring, do you see my calculator here, or? Maybe not, huh? So let me see. So if
yes, I can.
Oh, you can see. Okay, so if I do 1,060, the platen is going to be 170 ton, including the moving mass,
yeah,
the moving part. So you could go to 6.2 G, but as I said, for safety reason, we are developing a detailed nonlinear model of the reaction mass right now. It's going to take some time to have high confidence in this model and to see if we are before we go over the 680, because we have already applied 680 under 1 degree of freedom. So now if you apply 680 divided by 170, so you have 4 G's if the platen is empty, right? If the platen is empty,
I see.
If you have a mass of let's say 400 ton, so 680 divided by 400 ton, which is a very large specimen. So 570, 400 plus 170. So now you have 1.2 G.
Wow, fantastic. Thank you very much.
We'll be able to go higher than that. I don't think we'll go to the full 1060.
Yeah, thank you very much, Professor.
You're welcome.
Excellent. There's one more question from Akash. Go right ahead and unmute yourself and ask away. And then.
Thank you, Kurosh.
Yep.
Morning, Akash. Yes.
Hi, Professor Conte. So my question is, do you need to repeat the tuning again when you assemble the structure on top of the shake table? Or so I think you mentioned you do the tuning. Was it using the empty shake table, or
Yeah,
We also
it's a good question. So you see my screen, right, Kurosh?
yeah.
Yeah, so let's see, let's go back to here. Right, so this tuning process that I showed here, it's we do it when the table is empty. The research team, we ask them to send us their earthquake record that they want to play. For 1D, it was easy to check them against the limitation of the platen. Now for the LH post 6, it's going to be much more involved to check this motion, right? So because we have to look at the combination, you know, in different degrees of freedom and so on. And so in the past, we would tune the table when it's empty. Then the research team comes and build a specimen. And let's say that it takes two months, then the instrument for 1 month, 3 months. So, and then at 3 months, we play the record. We use the same drive file as we had when it was empty. In reality, the system has changed. Now the controller has to control the specimen coupled with the platen. For most specimen that we tested in the past, especially building specimen, where if you think about it, the mass is only at the floor level. Between floors, there is no mass, just air. They are relatively light. You know, a few 100-ton specimen, 100-ton, 200-ton, even 300, it's still, you know, if we do it that way, it's still very good. The reproduction capability that I showed you here was done just like that. We tuned the table when it was empty, and then we just applied the same drive file. Now, if we have a specimen like with the big box, right, of soil, they are the heaviest specimen. We had this one here filled at maybe 3/4 at some point when we had this test here, I think was about 1,000 ton. That's the highest specimen that we ever had, which is still only half our maximum vertical payload capacity. So 1,000 ton, it would move the oil column frequency, you know, to a different position, right? But the oil column frequency, it is controlled by the delta pressure feedback gain, right? So the table will sense by itself, you know, that the oil column frequency has shifted, so to speak, right? So if we use a notch filter, because sometimes we have to use it's more ad hoc. If we struggle with just only the delta pressure feedback, we also want a notch filter. Then what we do is we would play a very small white noise, you know, with this, let's say 1,000 ton specimen. Of course, we take risk when we do this, because if we lose control, when we play something that we didn't have in mind to play, we lose the whole specimen, you know, for doing this. So we very carefully play a low intensity white noise. We get the new oil column frequency, and then we go and apply another notch filter, you know, at that new oil column frequency. We have done this a few times, but more and more, it is better to control the oil column frequencies using, you know, the delta pressure feedback if we can. And if we can, it's all natural. You know, if the specimen changes, it just accommodate for that. And then MTS is always developing their controller, and they have now an option that we have not checked yet, but it's an option that even accounts for the evolution of the specimen over time during an earthquake. You know, it starts by being undamaged at the beginning, so very, you know, it has its stiffest condition at the beginning, and then with the evolution and progression of damage, it becomes softer and softer. They have options that I think, from what I've heard, I talked to Brad Thurn of MTS, he's an expert in this. I think they tested some of these at the University of Nevada at Reno. It seems promising.
Mhm. So somehow the properties, the mass and stiffness of the payload also enters the control loop somehow, and
Yeah.
parameters can be updated. That's what
Yeah, there is definitely table, interaction between the platen and the specimen.
Mhm.
But from what we have seen in the past, it has not affected the control, the fidelity in the control very much.
Mhm. Yeah, thank you.
For those who are interested, we in the past, when we had 1 degree of freedom, we developed a full nonlinear model of the shake table with the servo valve, the actuators, the pressure supply, the dynamics of the platen. And this model has been published last year in Earthquake Engineering Structural Dynamics, including, we had identified and validated some model for the dissipation forces of the platen. Some is Coulomb friction related, some is nonlinear viscous. And people who would need this model for their research, they could ask us, and we would be happy to share it. And now we are extending this model to the 6 degree of freedom LH post. And what we do is we put MTS controller in our model. So we replace the real shake table by our model. And then we have the same MTS controller. We are still developing the model, but now with the acceptance test data that I showed you, we can see how good our model is. And we would be, of course, it's a PhD student developing this, but once it's published, we would be happy to also share this model with future users of the table.
Okay, thank you very much. We have a few questions in the Q&A and another hand raised. Let's go ahead and take care of the hand that's been raised. Davide, please go right ahead and ask your question, and then we'll get to the Q&A questions because we're kind of running short on time as well.
Hello again. Yes, I would have another question, and about the system used for to increase the size of in plan of the prototype out of the shaking table. And this is very interesting. And actually, I was wondering, so I'm curious about the possible extension of this system to the rotational degrees of freedom.
Yeah, of course, it's a natural question. And let me just, let's see, where was it here? Right, so we have already, internally discussed this, and some of my colleagues have already actually designed something and analyzed it. So once you have the vertical and the rotation, we cannot anymore have, you see these long beams here. They were sliding on low friction devices, but of course they were always remaining at the same height. Now with the vertical degree of freedom and the rotational, we would need what we would call a base frame. Very, very light and stiff. So it's very challenging, right? A base frame that, because now the platen, let me show another figure. This one. So the platen right now, it goes up 5.5 inches, and then it's at the neutral position. And from there, it can go plus or minus 5 inches, plus or minus 15 or 13 centimeters, right? So now we would need a base frame, right? That would basically cantilever out. Let me see if I can. A big frame like that, a truss type frame that is not adding too much mass, but a lot of stiffness. And we would need to do a lot of modeling and simulation of specimen, that sits on top of this, and make sure that it is stiff enough so that the boundary condition are similar as if it was just the platen
Mhm.
extended, all the way. And we need to organize a workshop that we are going to do very soon to discuss this need and the kind of design that could, deliver something that is good.
And I guess this.
Once we have the workshop, potentially we would, write a proposal to get it funded and build it. So sorry, David, I cut you off.
Sorry. Yes, and so I guess that this frame useful to carry out very large experimental tests may be used also for large problems in geotechnical engineering. So for soil structure systems, for instance, I guess.
Yeah, of course, right. I think you have in mind maybe what if you wanted to test a portion of a bridge with the abutment at the end of the bridge, right? The kind of a sub system of a bridge.
Too many ideas, Professor. Thank you. Thank you very much.
Yeah.
All right, thank you. So the first question in the Q&A is, how does this table compare with the e-defense table?
Okay, so let me go back. From what I remember, I checked it recently, so let me see. So the e-defense table, we have, you see, 12.2 meters and 7.6 meters. They have 20 meters by 15. It's gigantic, their platen. But if you think about what we just discussed, if we find a way to have a universal base frame cantilevering out that works, at least for 1 degree of freedom, we were able to do this, right? But it was easier. It's not necessarily a big handicap compared to them, right? Then here they have plus or minus 1 meter. We have plus or minus 90 centimeters. They also have plus or minus 1 meter here. We have plus or minus 38 centimeters, right? So we lose a lot, but ground motion, if you measure ground motion and so on, they always have principal directions, right? There is a principal axis and then where you have the largest ground motion, and perpendicular to it, usually it's significantly smaller. So to have the same capability on both axes, we don't see it as a high requirement. Now here, yeah, they are much bigger. They have plus or minus 50 centimeters, if I remember correctly, half a meter. We have plus or minus 13 centimeters. The velocity, they have 2 meters per second here. We are larger. They have also 2 here. We are the same. Here they have 0.7, I believe, meter per second. Now the maximum forces, this I don't remember. And the rotation, I don't know. I've never seen it. I think they don't make use of their rotation. Other comparison that I could make is the first time around, we received $6.4 million for the National Science Foundation to build the facility, because we have a blast facility that also makes use of the pump that was at the time, it was after 9/11. There was a lot of research in blast needed. Some of my colleagues, they had gotten a grant of 3.6 million from TSWIG. It's a part of Congress, it's part of the US government. So 3.6 and 6.4 was $10 million. When we changed the vertical actuator in 2009, we had pressure balance bearing and we put vertical actuator, was $1.9 million, let's say $2 million. So it's 12 million now. And now the upgrade, we got about almost 17 million from the National Science Foundation, and UCSD provided some resources up to 20, so 20 million. So 20 and 12 is 32 million. That's what we paid to have the 6 degree of freedom here. In Japan, they spent 600 million, and I've heard rumors that maybe even closer to $700 million. So you see, it's a factor 20 in the cost. Of course, they had a gigantic reaction mass. I think they have soft soil condition. Here we have a reaction mass of only 4,500 ton. In Japan, it's probably 15 to 20 times that. So that, I hope it answers your question. We could spend more time comparing other things, but I don't remember these other things.
Thank you very much. In the interest of time, let's go through these last two questions and then we can continue. The first question would be, which is the mechanism of generating the rotation, the z-axis of the shake table?
The rotation z-axis, so let's see. Let's go here. So you mean the yaw, right? The yaw. The rotation about the z-axis, Kurosh?
You're on mute, Kurosh. Yes, that's I think what the intent is, Joel.
So
Yes.
it's about the z-axis, right?
Yes.
So
yes.
for us, x is this, right? X-axis is this, and then right, the y-axis is here. Say this is the y-axis, and then the z-axis would be the vertical axis. So the mechanism to do the rotation about the vertical axis is only through the V-shaped horizontal actuator, right? The V-shaped horizontal actuator, they allow to move in the X, Y, and the yaw. So if we had not done anything with the vertical actuators, if we had not equipped them with servo valve for dynamic for dynamic motion, we would have, and we would have only bought 2 new horizontal actuators. So we have 4. We would have X, Y, and the yaw, the rotation about the vertical axis. And this, I think we can do 4 degrees. So it's basically here limited to have, you know, the end of the bumpers moving 15 inches north here and 15 inches south here. Does it answer your question?
All right. Thank you. The last question is, can you elaborate on the effect of the noise coming from the table's vibration on the test structure? I heard you said it only has effect if the structure is stiff. Would a typical brace frame stiffness be close to that threshold?
Could you, I wonder if by noise they mean this noise that I've shown here or something else?
Yes, that noise that you've shown there.
That noise, I see. So that noise here comes from 60 or 80 hertz, you know, it's either a vibration mode of the platen, a vertical vibration modes of the platen, or it could also be related to the oil column stiffness of the vertical actuator, which are very, very stiff, right? The oil column is very short and very, very large cross section. So the question is if it would affect, Kurosh, can you remind me again, if it would affect a test, a specimen?
Yes, if it would affect, if it would have an effect if the structure is stiff, would a typical braced frame stiffness be close to that threshold?
I mean, the specimen that we have tested in the past, none of them would have been, you know, affected by that. I doubt. Of course, some higher frequency modes that do not contribute much to the response may. For example, now you will hear tomorrow a discussion about testing some nuclear casks containing, you know, a surrogate for nuclear. Gosh, how do we call this? nuclear spent fuel, that is a little fragment of uranium that is in tubes that have a diameter of 12 inches, that are very long and have multiple support. So now we are looking into maybe for this, it could, we are hoping it will not have effect on that. That's what we are looking at, this high frequency vibration of very small tubes, steel tubes that will be inside the nuclear casks. But for building model of the kind of scale that we are testing here, I doubt. But of course, we cannot say never, right? We have to see. And we hope to find ways to decrease these effects. I remember 20 years ago when we had the shake table, we were controlling it for the first time, with the knowledge gained and the feedback to MTS, who could improve the controller, and also the experience of the shake table operator over the years, the fidelity in reproduction of signal has increased significantly. So I expect some similar phenomena with the 6 degrees of freedom. We will learn more and more and know how to decrease even more, the effect of these high frequencies here.
Great, thank you so much. I think that was the end of the questions, and we're actually a little bit behind schedule, so we can continue on with the next presentation.
So basically we have used the break, right, Kurosh?
Right.
Okay. Hopefully you attendees had the chance to listen and drink a coffee and eat some nice cake. But yeah, we will continue now. And the next presentation will be by Professor Tara Hutchinson, a co-PI of NHERI at UCSD. She will talk about preparing an NSF proposal to utilize NHERI at UC San Diego. We should give up my screen here.
Okay, great. Thank you, Joel. Thank you, Kurosh. Can you hear me okay?
Yes.
Okay, great. Thanks for the confirmation. Yep. Hopefully you can have a coffee while we chat about this topic. But the questions were so interesting. Yeah, thank you very much for joining us in this workshop. Let me put the pointer on. Is it pointer? Okay.
We can't see your screen yet, Tara. I'm not sure if you started sharing or not.
Oh, okay. My screen, I can. Thanks for that. Now you can see it. Oops. Oh, PowerPoint closed. Okay, maybe that's why. Sorry about that. That's a nice crash I just got. Apologies.
In the meantime, again, just a reminder, if anyone has any questions, raise your hand, put it in the chat or the Q&A, and we'll get to it as soon as we can. And thanks again for all the questions earlier. Really useful.
Yeah, I apologize. PowerPoint tool just crashed, so it's rebooting. Let's see. Okay, let's try it again. Can you see the screen okay?
Great.
Okay, great. I'm sorry about that. Well, thank you very much for joining us for the workshop. We really appreciate your attendance, and we know everyone is busy, and we're just before the holiday season, so taking the time to join us is really wonderful. We've offered these workshops annually for many years now, and we anticipate and we hope, of course, that amongst curiosity and innate interest in the facility, one of your primary reasons for attending the workshop is your interest in preparing a proposal to the National Science Foundation to use the facility. We're all passionate about its capabilities, and we hope that we can give you some, let's say, best practices regarding proposal and planning activities. So this talk is sort of geared to compile some of these thoughts and assist you in this proposal effort. I've organized this around four sort of steps, I suppose. First is to define your project vision, some of the elements we think are important for that definition. Some thoughts on selecting your team, thinking about your schedule, and estimating your budget. And I've drawn from my own personal experience in two particular projects I've been involved with that, of course, utilize the facility in its unidirectional capability. But I learned a lot through that process, and something's good, something's bad. But I try to focus a little bit here, in particular around the central activity of your test planning along these thematic key steps. So let's talk about the vision, the test purpose, and the impact. Really, we all as researchers need to think carefully about this and articulate this in our proposal. The recognition is that these tests are large, they're costly, and they're large, and they're costly. They'll take immense time and resources. So by the nature of our desire to utilize such a facility, we can be proud that our experimental program and the ensuing complementary efforts will be of a landmark, effort or contribution to our field. They're really completely unique, and they support some broad visions to solve what we often refer to as grand challenge research problems in the earthquake engineering community. So in your definition, after defining your project vision, you want to certainly articulate how the test program helps you address your project vision, what its purpose is, what mechanisms perhaps that you anticipate will dominate the response of the particular system or systems that you're envisioning testing. I think this will help you sell your vision and know what to measure, what to track, what your protocol might be. It'll also help you identify the key gaps in knowledge, locating it relative to past research or limitations in design codes, maybe methods, standards of practice, or modeling capabilities. We do believe pretty firmly that in articulating your vision, the impact of your experimental program will be significantly extenuated if you incorporate a robust modeling or simulation activity, and if you integrate that with either leveraging and or building upon the development of some type of design standard. It might be something you want to validate an existing, or maybe advance a new, or extend a current design challenge in practice. Here's an example of a test program overview. We performed a 3-phased full-scale test program. We often go back to this program. We looked at a 5-story building NCS system. The vision for us in very short form was, how can we understand a total building system's seismic response? And so in order to do that, we erected, the central activity was to construct a important place concrete moment frame building and integrate within it a wide variety, as best we could, of non-structural components and systems that were standalone, that interacted with the structural system, and that interacted with each other. So that in the end, this was really a total building system. That was the short project vision. And then, of course, we sat down and we wrote down very verbosely what we felt were the project vision's quite extenuatingly. I won't read them here, but we tried to check the box on each as we prepared our proposal and our test program. You'll notice that if you read through these, they focus on the data, but they also focus on the modeling and the simulation tools. Actually, Professor Conte worked pretty extenuatingly on developing new simulation tools in this project and how they could link back into performance codes and performance-based seismic design tools. And so the last important point for us, and we had a pretty extenuated group of colleagues from industry and practice that helped us assure that we could tailor our design of our testing and our modeling so that the findings could make their way, or key and important findings could make their way into seismic design guidelines and codes. So this actual last statement was a part of our overall project vision from the start when we wrote our proposal. We identified our, let's say, hopeful impact, took that vision and sat down and tried to articulate it in the context of the National Science Foundation merit review criteria. If anyone's been on proposal review panels, of course, addressing these areas of both intellectual impacts and broader impacts is something we as the scholar, as a researcher seeking out research funding and support for our ideas needs to very clearly articulate. And over the years, I continue to go back to the NSF criteria, which is, it's updated fairly regularly. So going back to the proposal and grant guide, I think this is the latest version here, 22001. That'll help you, of course, write detailed intellectual and broader impacts statements quite succinctly into your proposal. So choosing your project team, the second step, these are complex, large test projects. So, assuring that we have a variety of input and support, not only our academic colleagues, including our PIs and grad students and undergrad students, but also industry partners and our staff. Our technical staff here are available to you, and they have a breadth of experience in a wide range of projects, but also at your own home university. You may have a laboratory there, or you may have other technical staff across different disciplines that you're planning on working with, and collecting their information and working with them or making them an integral part of your project team is certainly something quite wise to do up front. Here's an example of one of the projects I was involved with, the cold-formed steel mid-rise building project. You can see, a nice group of folks here, but just to break it down for you, we had 3 PIs from 2 different universities, 2 graduate students, and 8 industry partners, and then only shown here are 2 of our technical staff. There were a number of others that assisted along the way in various parts of the project. So our project team was quite broad in terms of their expertise and disciplinary background and their profession. And each brought a very interesting and important element to the project. So there are, amongst the project team, there are certainly project leaders. And during the active time on site, it's really those researchers that are on site amongst yourself, including your graduate students and or your postdocs and undergraduate students, helping to manage project resources and achieve deliverable timelines, coordinating with suppliers and contractors, equipment vendors, working closely with our NHERI staff. So before coming to UCSD, planning some of this out, thinking about the schedule, preparing CAD drawings, performing pretest analysis to help you select motions, make decisions regarding instrumentation layout, and even preparing either MathCAD or MATLAB sheets in advance. And I think Professor Mosqueda talked about this with the new availability of the Jupyter Notebook. This is a fantastic opportunity. He's doing something like this, he mentioned, for our modular testbed building with a few students, so these tools are available for us right when we get started testing, and all we have to do is very, very quickly download the data, and then the processing tools are available to help guide us during the very intense time of testing. So there's sort of several tiers of possible preparatory modeling and analysis pages that we can prepare before we come to UCSD. When we're there, we're going to be busy with instrumentation and cameras, both analog and digital instrumentation, and all of the day-to-day activities such as tooling and labeling, oversight, and participating in construction and preparing for the testing. So those project leaders, namely our grads, often our grad students, our undergrad students, or postdocs are going to take on the lion's share and the burden of this and be very active. And we want to plan for that in our research proposal. And then Professor Van den Eyn mentioned industry partners. In all the projects I've been involved in, whether they've been out at our shake table or laboratory projects on our main campus, a wealth of knowledge and breadth of discussions, can be quite fruitful. But as well, our industry sponsors, they see on a day-to-day basis what's happening with their product, with its installation, with its design. They can help us identify challenges in the field, practical challenges in the field. They may steer the discussion in terms of research objectives. They may take a back seat, but provide you their materials and allow you to move it forward and exercise it in a testing environment. And I show this slide here because we had over 30 or so industry partners in the BNCS project. They came from a wide range of disciplinary areas. You see folks that are involved with designing, constructing stairs, to anchors and fastening systems, to HVAC systems. And in this red box, you also see folks that are actually manufacturing hospital equipment. So we had an element of that particular test program that looked to investigate the performance of a hospital setting and hospital equipment. And so we certainly had to reach out to that community, and that may not be their forte, but they can learn a lot from us and we can learn a lot from them regarding the needs, the functional needs and resiliency of their equipment in the setting that it needs to operate. So those partners were integral actually to making decisions regarding our hospital layouts and design of scenario hospital configurations. So maybe something quite unexpected, I would say. Also on your team, as Professor Conte mentioned, we have a wonderful group of on-site technical staff. You've gotten to hear from Dr. Karush Losvide today, of course, helping us organize. Thank you so much, Karush. But as well, we have a site foreman and development technician, an R&D engineer, and all things IT folks on the site that have been there largely through the inception of the site and our breadth of resources. And we have many animals on site, I should mention. This is a snapshot, of course, of someone running across during a construction project, helping with construction supervision. Don't count on them, though. Developing your schedule was the third bullet for consideration in preparing your proposal. Think about the major items during the proposal level, things like test planning, setting aside time for that and resources for that. Think about your on-site test efforts. The duration for that can vary significantly. For one of the projects I was involved with, BNCS, we were on site for more than a year. For another project, we were on site, physically demanding and intense on site for about 5 weeks. And in like fashion, instrumentation can vary. We can have 200 sensors to upwards now of 700 sensors. We want to set aside the time for that. And at least in the proposal stage, a general sense of the range of sensors and the types of sensors. You want to look at the inventory. And I have a slide at the end, which points you to our resources on the Design Safe site, which we've helped to disseminate, where you can find the latest sensor inventory. And I believe tomorrow, Karush is going to speak about the new data acquisition system and the available inventory to even allude further. Test execution, this as well can vary significantly. We have to think about our protocol. What are our objectives? Are we testing in one configuration? Are we repairing now with the multi-degree of freedom capabilities of the table? Are we testing sequentially? Are we initially going to use all degrees of freedom of the table, only the translational degrees of freedom? We have to think this through relative to our specimen and its objectives. Finally, the on-site test efforts. Don't forget about demolition. It has to be in your schedule and in your budget. It can take several weeks, and it can be upwards of hundreds of thousands of dollars, depending upon the complexity of your specimen. No, some reason okay. Post-test data processing, post-test modeling, and technology transfer are all things that should be in your schedule as well. Data processing is almost proportional to the number of data channels you have, but it's also needs to be thought through relative to what your objective is in terms of processing the data. And there may be several gradations or tiers to the fineness of the processing that you need to do before you can get to a point where your data is seeing significant utility in terms of validating or extending computational models. So very dependent upon the type of specimen you're aiming for. The final point there about technology transfer, really set aside some time for this. Of course, it's an ongoing activity, but I put here, it's really the K through gray audience, I suppose. It could be outreach just at the younger level that you're interested in as one particular activity. Maybe that's something that's done on site, and Professor Van den Nijn offered some ideas there of what's been done on site in the past, what we've done as an operations group, or what we've seen folks do, what she's led, for example, just to the younger audiences. To stimulate them and get them excited. Leveraging from your project can be a great opportunity to do that. And of course, the National Science Foundation looks at us favorably when we're able to take the time to do that, but it needs to be in your schedule and you need to think about it from a resource perspective. And then, of course, the grayer audience is extenuating it out to not only the public, but the professional audience, having that time. In past projects, I've been fortunate. We've always had some close connection with industry standards boards, folks that are writing guidelines and see particular missing links in the guidelines and things they'd like to get out of the test to enrich, infuse, or improve standards of practice or guidelines. So thinking about your technology transfer as your central activity of experiments runs through, as well as your modeling and your overall projects continue, are certainly important. Developing your schedule, there's now really much thought that we need to break down in terms of the actual on-site efforts at the start of the project. It's going to be different than beyond the project. So when we're let's say we're successful, we need to think about maybe some rough planning by year and quarter. The year prior, we have to narrow in on the quarter where we're going to be active. Several months before, of course, we're going to have to produce detailed specimen drawings, a test protocol, select motions, and Professor Conte talked about the strategy for iterating and obtaining, providing the site with test motions and iterating, utilizing those test motions, what the site can do to facilitate the generation of those motions. So we need to think about that as a researcher and provide the site, have active discussions with the site, and provide the site with the motions that are intended, including the intended scale factors. Finally, developing instrumentation plans. As we get very close to physically being on site, we need to provide the site with those instrumentation plans. We'll often request a presentation to NHERI staff. When is highly dependent upon the complexity of the project. But this, of course, is extremely important to solicit input on the planning, planning preparation phases, what our plan is in terms of construction, and attachment to the table, mass assembly and attachment, and instrumentation. These are clearly, and then test execution phases, presenting what our idea is there and what our test completion or sort of wrap-up plans are for the de-erection and disposal of the specimen. And the most important point from the NHERI staff's perspective, site's perspective, is a critical point from their perspective is to assure that proper safety protocols are in place. These are very large, very heavy, and critical specimens. So we will solicit, offer input to the researchers prior to arriving on site to assure that the specimen will not be a danger to the facility or surrounding staff. Here's some examples of on-site scheduling efforts for a cold form seal project I was involved with. We started construction and undertook all the major construction items within about 4 or 5 weeks. We installed instrumentation across a period of about 3 weeks. We spent about a week, a very, very intense week of conducting seismic tests. We had a component in this program to undertake live fire tests. You see the photograph here. Live fire tests were performed at 2 floors of the test building. So in order to do that, we needed to budget in a week to remove seismic sensors. And finally, we undertook those live fire tests. In total, we expended about 12 weeks of time on site for this construction and testing these items up above. And then we had about a week of de-erection. This was a prefabricated building structure, and so it was quite rapid in terms of its de-erection. But every, oops, it's not going to let me start that. Every test is a little bit different. Let's see if I can start this. The construction duration greatly varies. Construction duration greatly varies. And so with this particular specimen, we were fortunate. The lower floor of the specimen was stick framed. You can see the attachment to the table being undertaken now. And the single placement of studs sequentially and framing and ledgers coming into play. However, the upper floors, let me just fast forward it a little bit too much. The upper floors were prefabricated off-site, supplemental masses were drawn in individually, and now you can see the panelized construction being undertaken quite quickly. The lower floors of the structure, I think the lower floor, which was stick frame, took 3 to 4 days, whereas the upper floors, upper five floors of the structure took just, I think, 3 days in total for a much more significant elevation gain, obviously. So as well, construction duration varies significantly, and so does demolition. Here's a little time lapse that was generated for the demolition of that structure. So now it's been tested. You can tell it's been tested. It developed a soft starting mechanism. At the second floor, you can see a slight lean to the structure, and you can see some of the superficial fire damage at the exterior. And now we're demolishing this structure piece by piece. Since it's panelized, again, it took less than 1 week to de-erect the structure. I believe it's 2 to 3 days just to get down to that lower floor. So those are all things we had to think about. We hadn't envisioned originally that the lower floor would be stick framed, but due to the attachment of the table, that ended up being the easiest thing to do. And that wasn't something we had thought through until we looked more carefully about the attachment to the table and the strategies, particularly for carrying the overturning loads to the tie rod assemblies available to us at the table. So that changed our thought process a little bit. Here's another example of on-site efforts and the dramatic difference in scheduling. This was for the BNCS concrete moment frame building. You can see we started in June 2011, and we ended in September. And at that point, we had just a bare superstructure. So 3 months and some change there just for the bare superstructure. And then we needed many months beyond that to install the non-structural systems, which were central to that project. So a few tips regarding maybe some research activities you might consider pursuing during construction, since we're on the topic of during construction. As a research team, you're going to be really multitasking. You're going to be performing pretest simulations. You're still thinking about your protocol, refining your protocol. My advice, I guess, through the experiences I've had is watching and documenting and taking part as feasible in the construction is extremely important. And one thing we did in one of my projects was we created a weekly construction log documenting all the construction activities. So, it would be what the activities were and what the outlook was for the coming week. And, and of course, you're going to take lots of photographs as things are being, installed and being brought onto the site. But this tended to be a central part of our discussions every week or every few days. And actually that data is now available because we were on week 40 plus or so as we approached the finalization of that project. An actual schedule can be very different. And since we're thinking about proposals, here's an example of a multi-year actual schedule, maybe of the major items as related to this project BNCS that I mentioned. We started with some pre-proposal workshops in, I think, 2007, and then we had the idea, it's inception of an idea. And then we built that idea up, started to write a proposal, but needed some more input from industry. So we had another workshop in 2008. A year later, we were funded, we were happy, and the National Science Foundation funded the project. And then then we had our kickoff meeting, and we began to get to work, for a year and a half in planning. Finally, the full construction time lapse about nine months or so. And then, just a very short 1 month of seismic testing, sequentially in about the middle of 2012. And finally, immediately afterwards, we conducted live fire tests also for a few weeks on that particular specimen. And then the test was over. So we de-erected this specimen. And in the meantime, life is going on. I had our first son in 2007, had our second son in 2011, and was crawling around a test specimen just before it began its erection. And then the kids are grown. But now the data is available. So there's a silver lining, and the realities of life were intertwined with the professional activities of an actual schedule, which was quite sensitized us all due to its length, but I think quite rewarding. Estimating our budget was the last item here. I broke this down into some thoughts regarding research staff, tests, and maybe a bit about travel and workshops, some suggestions here. The research staff is really your PIs and your students and your postdocs, envisioned to carry out the tests, modeling, guide the project. The question clearly is how many and for how long. The projects I've been involved with, we've each had our sort of definitive role, and maybe a grad student working with each of us. Resources are scarce though, so we had to be practical about the scope of each researcher's activities. The tests, there are physical test costs. I can't say enough that very important to look out towards industry in particular, and or other granting agencies. The National Science Foundation budgets, can be prohibitive in terms of supporting the physical test costs and the construction of the specimen. We were fortunate in the past to partner with several different industry entities. I showed you one slide where we had over 30 industry partners. Each of them brought not only their product, their design, and their input to the project, but in many cases, there's a physical cost to integrating their element into the test program. And so we try to do our level best and estimate it. And they also brought, as a consequence, cash resources to bear to support the execution and the integration of their element into the program. So those test costs can vary dramatically. I have some ideas, I think, on the next slide as well. And then think about travel and workshops. We're all not traveling very much right now during this pandemic, but you certainly will want to travel to UCSD and take part in your tests, and your grad students will as well, and your partners, your PIs. So some thought process into how much travel funds you might need and what the purpose will be. My last comment here is that in terms of preparing a budget, really your budget is heavily linked to the duration, the scope of the tests, and any additional support you can garner, additional outside of the NSF resources. Let's see. We often get this question since we have some, we are funded as for operations and maintenance through the National Science Foundation. We often get this question regarding what the site will cover. What is included in our operations and maintenance resources. The site will support operations during construction and de-erection. That means, guidance regarding test planning and oversight during construction and de-erection and execution of tests. The site is not able to support your actual construction costs and your de-erection costs or your disposal costs. You need a separate budget for this. So, advice I've given to colleagues in the past: select several contractors, request some estimates. If you have a preliminary skeleton of your specimen, we did this recently for the modular testbed building. I'll show you tomorrow. We'll talk about tomorrow. We had several contractors and erectors offer us bids for that, and we were able to put a reasonable number in our budget, I think. For initial planning budgeting, we suggest, seeking out UCSD vendor contractors. If it's going to be local, you're not going to bring a crew in. We have some suggestions. We can provide you some suggestions. The site will provide and support placement of all major sensors. So analog sensors, camera systems. Check the inventory against your needs. They will not support expendables, however. And I think Professor Conte mentioned this, but obviously strain gauges are expendable. We don't have them in stock, so you'll have to estimate how many you might need and put that in your budget. Cabling and labels, any unique brackets. We have a lot of this on site, but anything you think that might be unique to your instrumentation and the placement of your instrumentation relative to your component, you should really think that through, and set aside some resources for it. Damaged sensors and cables, that's certainly possible, and setting aside some resources in the event that sensors are damaged so that you can replace them will be important and help the site. Here's some additional resources. If you go to Design Safe here, I won't go to this link, but it's in the slides. We've put together some information regarding recharge rates in particular for heavy equipment on site or our staff on site. A little bit about local contractors, local contractor contacts. So if you need bids on certain elements, there's a list of sensors, et cetera. So those three in particular might be useful for you in your planning and proposal writing. Expect the unexpected. When we decided to perform live fire tests on this cold form steel building, I asked Robert Beckley if he would install cameras. I thought they were far enough away on these safety towers here, and was pretty unhappy. He was pretty unhappy. And of course I was unhappy as well. The thermal loads were so high that, even I think 15 feet away or so here, we damaged the heat shield on these cameras. We also did some experiments with GoPros and thought that we had enough water overhead and placed these in water, and had done these in the NIST lab, but the temperatures and the placements of where we placed them in the room caused a significant evaporation of the water, and these GoPros and their shields melted as well. So we lost a few cameras in the process, and needed to replace them as a part of that project. These are some examples of testing scope and project resources, slightly different testing scope associated with the BNCS project. I won't go through this in the interest of time. Just one last thought here. In your NSF proposal, and Professor Van denIjn gave a nice overview of elements that we've seen we've either conducted here ourselves or helped folks with, but in terms of education and outreach. But I like to maybe think of three different categories of activities. I think we have experience here and have seen folks really be successful on the eco side when they think through some type of technology transfer activity. This could be, nowadays as simple as preparing webinars, preparing specific project videos, or maybe offering laboratory tours, working closely with media relations. And we offer some contacts here at our School of Engineering. Of course, we know our colleagues have their own internal contacts, but this is local. And then, overall thinking about how we might educate the future engineers is really reaching that younger audience. I've found that over the years, the ideas I have can fit in any of these. I share with you these couple of photographs on the right side here, where we were able to bring out search and rescue crew who inspected a test structure, one of the test structures, and actually used it as a training ground for their younger firefighters and urban search and rescue crew. And it wasn't something we had anticipated, but it landed itself on a very valuable opportunity for outreaching to a community we hadn't really thought would take much interest. Let's see, some last remarks. I think the staff here is amazing. Our PIs and co-PIs are available to help with all your proposal planning and project execution. We recommend that you discuss during the proposal preparation, help to, as you begin to develop the scope and the budget. We guarantee you that all of our conversations will be kept confidential. We want you to succeed. Your success is our success. The actual level of early interactions, one of my last comments here, during the project planning with us is up to you. But again, we want you to succeed. So my parting words, please reach out. And the fact that you're here and listening in, tuning into us, certainly shows us that you're interested in looking for insight into your preparation and planning. So with that, I'll conclude.
Thank you very much, Tara. So do we have any question?
Not at this time. As a reminder, please raise your hand to unmute and ask your questions, or just place them in the chat or the Q&A and we'll get to them.
And if some question develop, then we will have again a Q&A after Professor Restrepo's presentation. Actually, no, yeah, after his presentation. There is one comment I would make. I was at a technology transfer, NHERI Technology Transfer Committee just before NHERI COVID started, and it was very interesting to hear the discussion there. The young researcher among you who want to use the shake table and make some big tests and so on, like Tara mentioned, I would strongly encourage you to connect with some professional engineer with a lot of experience, intimately knowledgeable about the code. And this committee has developed a template, a pamphlet that would be highly useful. We're going to try to find it before the end of the workshop here and make it available. They even offer some free office hours. Some of the highly experienced professional engineers, some are recently retired. They'd like to be helping younger researchers. So because the process is very long, if you want to improve the code or propose a new design guidelines, it's a very, very long process, and you need to be to have the advice of people who have a lot of experience with that. So then, Kurosh, I guess we go with the walkthrough, or?
Yes, we can start with that. I will begin sharing that right now.
So we're going to present again a walkthrough to give you a little bit of a taste as if you were here in person. This was filmed a few weeks ago, so it's not exactly up to date, but not many things have changed since then. Things have changed inside the computer, inside the controller, and a few technical setbacks that we had to overcome. Good morning. My name is Joel Conte. I'm the PI of the NHERI experimental facility at the University of California at San Diego. We are now in the final stretch of the upgrade of this facility to 6 degrees of freedom, and I'm going to give you a short tour of the facility. So here we are in front of our large staging slab that you can see here. You can see some formwork. We just poured the foundation of the reconfigurable modular testbed building, which is the first specimen that we will test on the upgraded shake table in late January. You can see a few things here too. These plates that you see here are modular floor diaphragms that will be part of this specimen. And then you also see some large steel plates there piled up. They will act as they will be used for added mass to satisfy similitude. You can also see behind the fence there some BRBs, buckling restraining braces that will be also part of the specimen. And now we are walking towards the shake table, the reaction mass. Last year when we did the walkthrough, you may remember that at the time the platen had been taken out of the reaction mass and was standing on 4 reinforced concrete columns here. Now it is back in the reaction mass. So here we are at a very good location at the northeast corner of the reaction mass, able to see a number of very interesting things. So first of all, you see the platen. Platen was taken out of the reaction mass in February 2020 and was brought back in April 2021. You can see the V-shaped horizontal actuators. We have the old actuator here and one of the 2 new ones there. You can see, you cannot see, but the swivel head of the old actuator had to be manufactured from scratch because of corrosion issues. And then the back swivel had to be refurbished. You also see these 2 wooden planks, circular, that are preventing water from penetrating into the swivels. We want to be very careful in the next 20 years to avoid the corrosion problem that we experienced. Of course, these wooden plates will be replaced by some steel plates, and we will have other protection system. You also see flexible hose going up from the red pressure pipe to the 2 servo valves, one on each side of the horizontal actuator. And then in the back of them, you have a set of flexible hose with the return fluid to the large blue pipe and back to the surge tank. You see also the very large steel plate at the base of each of the horizontal actuator, connecting them to the reaction mass. You actually see the old one here that was supporting one of the 2 horizontal actuator the last 15 or 17 years. You also see the crash protection system. You see one bumper here with a distance of exactly 15 inches between its piston and a large steel reaction plate with on top of it a sacrificial wear plate. You see one of the servo valve, the high-speed, high-flow servo valve of the northeast vertical actuator here with a smaller red and blue pipe. I saw the high-pressure fluid coming through the red pipe and the return fluid through the blue pipe. You see some inline actuators, inline accumulators, these vertical bottles here. You also see some large concrete planks. So these are the existing one that we had since the beginning of the facility. The top one will be reused. It's going to be spanning from this side to the other side of the reaction mass here. The second one, the rectangular one, that will be closing this portion here, could not be reused. It is too thick. It is too thick. Now that the horizontal actuator can move up and down, we had to remanufacture new ones made out of steel and concrete that are thinner. So we will bring these new planks here, and after that they will be spacing all around the platen on the east side, west side, north and south. And this spacing will be closed by what we call the steel covers. These large steel plates that will be hinged around the top plate of the platen and will be supported by a heavy-duty wheel, a cart wheel, that will be rolling either on the reaction mass or on the composite planks that will be here. So now we are seeing the roll degree of freedom in action. MTS is sending right now a random white noise along this roll degree of freedom. So you can see that the south edge of the platen is going up and down a couple of inches, and the same thing on the north side. Of course, this is produced by only the vertical actuators are active in this motion. So here to the south of the reaction mass and the platen, we have the hydraulic power building. At the bottom there, we have the controller in the room. The corner at the bottom, we have the controller of the shake table and the hydraulic power system. And upstairs, we have the control room from which the shake table is operated. Inside the building, we have the hydraulic power, the accumulator bank, the pumps that we're going to see in a minute. So in terms of hydraulic power, in the past, we had two hydraulic power units, two pumps that are located there on the east side of this building. We have refurbished them just in terms of we changed the heat exchangers. And now here you see the two new pumps. So now we have a total of 4 pumps, and 3 of these pumps are pressurizing the accumulator bank, and 1 is providing the pilot flow to all the horizontal and vertical actuators. We needed these 2 additional pumps because the accumulator banks had a capacity of 2,500 gallon. Now we went to 10,000 gallon, quadruple it. So we needed the additional pumps. You can see here the electrical feed into the pump in the silver pipes. In the back, you have the copper pipes for the cooling, the water cooling system. And now you see our new accumulator bank. In the past, we used to have a much smaller one that was located here. It had a capacity of 2,500 gallon. The bottles were much skinnier, not as tall. It's important to notice that we are at mid-height of the bottle here. There is 1 story below us. We have 15 groups of 5 bottles, so 75 bottles at 130 gallon each. They are filled with nitrogen. There is a piston at the bottom. When we pressurize the oil, we push the oil under the piston for about 20% of the capacity, so about 2,500 gallon of oil pressurized at 5,000 psi. And then when we play earthquake test, we release that oil, we blow down that oil through some blow down valves. It goes through the big red pipes that we saw earlier. It goes and feed all the horizontal and vertical actuators in the reaction mass. You also see that each bottle is equipped with a wireless pressure transducer they are all monitored remotely, continuous monitoring. So here we are on the 2nd story of the hydraulic power building. We can see a very nice overall view of, again, the accumulator bank. You can see the top of them here. We can see the 2 existing pumps here in the back. And very importantly, the surge tank. It's a 5,000 gallon surge tanks, which receives all the return oil coming back, from all the horizontal and vertical actuators. You can also see down here the 2 large red pipes that are going to the reaction mass. We used to have 1 of them in the past, had to double that. And then you can also see 2 large blue pipes bringing the oil back to the surge tank. And the smaller pipes are pilot pressure, pilot return, drain, and discharge. We also see, if we walk here, to this side of the surge tank, You can see in yellow 3 transfer pump. There is another one on the side there. They are bringing the oil from the surge tank to the reservoir of each HPU. And you also see an orange pump. It's the pump that transfer the oil from the surge tank to the heat exchanger that is located under my feet at the base there. We have now a heat exchanger to cool the oil from the surge tank. Now we are here at the east of the hydraulic power building. You see our new cooling tower, very large cooling tower here. We have 3 pumps. These are circulating the water, the cooling water, to the inside of the building to cool the 4 pumps and also to cool the oil in the surge tank. And then this pump here is to take water, warm water from the cooling tower here and pass it through the heat exchanger that you see between the 2 blue plates here and back to the cooling tower. And here we have our beautiful steel safety towers, 4 of them. They can be piled up 2 by 2 and reach a height of about 60 feet. And now if we come here, you can see these plates, steel plates, galvanized. These are the steel cover plates, right, to cover the spacing between the platen and the surrounding reaction mass and composite planks. You can see, for example, this one here. It is upside down. There is a casing here. See these 4 holes? Then the caster wheel will be bolted here. And the caster wheels just arrived. They are in this box here. Let me show you one of them. You can see that there are no miniature wheels. I can barely carry it. Look at the low friction, beautiful wheels. And this concludes our tour. Thank you very much for your attention. I hope that you can come and see it for yourself in the near future. Very good. Do we have any question at this time? No questions. So now I would like to introduce Professor Jose Restrepo. I think he's here. As I mentioned earlier, he was the first PI of NIS at UCSD. He led the design and construction of the whole infrastructure that you have seen now. And he's an expert in concrete structures and seismic design. So Jose, the floor is yours.
Hi, Joel. Hi, everyone. How many participants do we have here? And do you know the mix, associate, assisting professors?
We have 35, 28 attendees, actually. It is my impression that there is a majority of young researchers, but it's not so easy to tell.
Very good, thank you. So let me try to address. I have a few slides more than I usually do, but I try to do it in 30 minutes, starting 12 and probably finishing at about 12:35 or so. And all what I want to do, I saw the presentation of Professor Hutchinson, which was very informative, and I'm just going to give you some highlights, a little things of what we can do and some way of thinking, how to perhaps team up with industry groups with a clear objective can be to solve a clear identifiable problem or come up with solutions. There are 2 different roads that I'm going to show you here with 2 different projects that have something in common. So very briefly, the first part, I'm going to give you what I think could be grand challenges in structural earthquake engineering. and the way we are moving in the field in the past 20 years, and perhaps some experiences that I had in the island of Lombok in Indonesia doing some humanitarian work, that you can see that even there in these parts of the world, you can see complex problems in affecting the communities. So end to end, I'm going to dive into two case studies. They have in common building diaphragms. And one, it was the first one case study was the DSDM project that is aimed at solving a critical need for the precast concrete industry in the way of diaphragms, and ended up with the write-up of prescriptive requirements for ASC 7. And the second one is more of what we can say is a futuristic thinking of low damage. I think we are moving into low damage systems. And this one tries to minimize floor accelerations, for which diaphragms can be, diaphragms can be designed with lower forces, and so are the structural components. So even though there is commonality between those two projects, they have some distinct differences. And my idea is that the takeaway you have is that you know how to assemble a team and collaborate with peers. So even if you are going to lead or you're going to form a team, a strong team that you can go to NSF and put a strong proposal. So I had the opportunity to do some humanitarian work in the island of Lombok in Indonesia. And that was a couple of years ago. So this small island, which is east of Bali, experienced a swarm of earthquakes, some of them 6.4, 7, 6.2, 6.5, 6.9. And this is a small island, maybe the size is smaller than San Diego County for sure. It's densely populated. And there they lost many of the mosques where they were meant to group in the case of tsunami or earthquake. They came down catastrophically. They also, being an island, they're one of the main communication links is via the ferry terminals or so, and those were also lost. You can see they rely a little bit on tourism, although this island is not very, very touristic, but they do have a little bit of tourism, but they export a lot of goods into other islands, and these transportation links were completely lost. Schools, you can see here that there are non-structural elements. It's an area that we have done some work here. Several of us, Professor Hutchinson and Professor Mosqueda, came down because they were, their understanding of non-structural elements is primitive there. Perhaps the most important thing are the people, and you can see people hurt. And a year after the earthquake, when I visited, there were still people living on the streets. So because their houses collapsed and had not been rebuilt. So you can see mattresses on the streets and make up houses or so just for people. Interesting also is to see in this place that the government had built this refuge for tsunami and was heavily impacted by the earthquakes, render the center totally useful. You can see a high floor about 20 feet height. In the case of a wave, you know that Indonesia experienced the 2004 tsunami, large earthquake and tsunami, so they decided to build a lot of places near the coast where they can go up in the building, but those buildings did not work, unfortunately. You can see a lot of damage in the lap splices. They should have never had lap splices there, but also the flexibility of the building. It's in the case of the staircases, where you can see that they develop yield lines, and some of them came down here. You can see staircase has come down all the way, so you don't even have access to this building. So these interactions are actually very important to focus in interaction with the staircases, large complex buildings that you can test some parts of the building and then move into the models. Transportation systems like marine structures, very, very important. And I think they work in non-structural elements that some of us have worked and continue to work. They still require a lot of research. So some of the things that, as I mentioned before, the system behavior and system interactions, wherever you can see these interactions, they can lead into large projects that are complex, that involve multi-universities, some doing analysis, some doing component testing, some doing capstone testing. So looking at old and vulnerable systems where you want to assess them. Are our assessment tools okay? Are tools like ASC 41 too conservative or well calibrated? Can we test some of these things at the system level and verify, come up with models? I think those are areas that will suit very well some of the new research utilizing the shaking table. We continue to work in low damage, protective and smart systems. I think there is one, in my opinion, the day we get hit by a big earthquake in United States, we're going to be opening the road to low damage systems. This has happened in Japan and in Chile, in New Zealand, in particular in New Zealand, where low damage construction is taken over right now. As I mentioned, looking into non-structural components and contents, sensors, structural health monitoring. Can we now deploy sensors in buildings? Is there any way we can do that? Doing multi-hazard research, combining tsunami and structural research. And then model calibration. I think it's an area that we believe is for many, many years, even for the past 30 or 40 years, we've been saying that finite elements are going to solve all the problems. And every time we do a blind prediction, we find that we're still far from things. As far as complex system behavior, we can see the world going into skyscrapers, tall buildings with significant discontinuities and transfer diaphragms, tie-back effects, construction stages, top-down construction. How does it affect? What is the implications of that when you have pre-compressed slabs and beams? The structural irregularities, we begin to see some tall buildings that have increased irregularities and vertical offsets. It's the new trend these days, where our buildings tend to be in the Plaza Square these days, tend to have more architectural features. And finally, trying to understand a little bit more solid structure interaction, including at least 5 components of the ground motion if we eliminate the torsion, but rotational components of the ground motion can be important. Let me show you why. In this building, this is the Alto Rio building in Chile, which was quite narrow, very complex system, a lot of interaction with different elements with the slab, problems of shear, compressive strains. But more importantly is that there was a sensor in the close proximity of this building. And once we do analysis with different tools, we cannot still fully understand what triggered the collapse of this building, and could have been, or maybe the rotational component of the ground motion had some influence in the collapse of this building, and is yet to, it's a hypothesis we still need to solve. And the other one we have here, you can see the testing of the bridge column here. Very simple. This is the closest to a single degree of freedom you can have. It should be very easy to evaluate. And then when we look at blind predictions, like the one on the graph here, you see the different earthquakes, earthquake 1, 2, 3, 4, 5, 6, that we tested this column. And then we had the recorded displacements. We asked the community to predict the displacement of these columns. We can, unfortunately, we can see that we have the dispersion is very large. So this is an opportunity for you to better calibrate models, to call for blind predictions. And it's something I do encourage every one of you when you put a proposal, that you set aside some budget to do a blind prediction, invite the community and see if we can reduce the scatter of our predictive models. I think it surprises us that a simple model like this, which we think is pretty straightforward, we can have such differences in the responses or so. Then we go into low damage system. I'm going to leave the video running.
The success of the CREST program has been a defining event, which promises to propel seismic engineering, design, and science forward. What lies over the horizon?
It's always tempting to believe that we're just about finished all we need to do in earthquake engineering, but I suspect that people thought that in the 60s. The prediction was then there would be no more need for doing any testing in 10 years' time. Everything could be done by computers. 20 years after that, we started to build these large-scale testing facilities because we realized that, in fact, we weren't getting the answers from the analytical models that were adequate. So I would hesitate to say that we're getting close to really understanding the way that structures behave in earthquakes. I think we're very much further on than we were 20, 30 years ago, but I think there's still plenty of opportunity for young research students and young faculty members to cut their teeth on earthquake engineering problems.
And this is 20 years ago, a recording of Professor Nigel Priestley doing low damage systems. And you see that after 20 years, there's still plenty of room for you guys to move forward in research and either through calibration of models and experimental work. So now let me dive into the example projects. I'm going to be describing the diaphragm seismic design methodology and one what we call inertial force limiting floor anchorage systems. The second one is with Professor Giorgio Sampras, who's now a faculty with us, he's a colleague with us. They were multi-university projects led by the University of Arizona, both of them, Professor Robert Fleischman, and Lehigh University with our colleague, Richard Sauce. And again, with UCSD, fantastic team. In these teams, I hope if you have a great collaboration, you can build friendships that are going to be long lasting. We still have excellent communication between the PIs and those who were grad students then. It's important that you take these projects as a way of building community as well. They involve large-scale testing. They were not full-scale, but they were large-scale testing. Both of them were tested at 40% scale. Yeah, with a strong simulation concept. So it's basically you have the simulation, you have the component testing, and you have the capstone or final testing to prove that the concept that you intend to check works actually. In our projects, we love to have design consulting oversight, and every project I do will have a strong component, maybe 3-4 consulting engineers who are willing to give their time to support the project, and a lot of industry partners. So you see the industry partners in the next slide. In both of them, we have the topic are floor diagrams. So I'm not going to spend any time here, but the more people, many industry are willing to work with you in whatever aspect, maybe donating materials, maybe giving you input, selling you materials at cost or so. So here is part of the activities that we have in our meetings, including walking around. Actually, this is not far from the shaking table. And a lot of students in different areas, PhD students, master students, postdocs, REU students as well, all involved in these projects. So the first one is solving this problem that was observed in the Northridge earthquake, 2004. What happens to precast concrete diaphragms? They are not working, they cause the collapse of several structures in the Los Angeles area. So we try to work here all the way from the component to the system level. Here is the structure of, I'm not going to explain a lot of it, but it's the structure of the project with Robert Fleischman. And those days, I just love to place this one because we were young. Those days, this project actually started in about 2003. So it's about nearly 20 years ago. And it's solving these problems of the in-plane forces in diaphragms, connection, load paths, and so on. And you can see in Northridge, the inertia forces never got into the lateral system because there was no way to transfer this. The understanding of diaphragm action was primitive or poor then, and that created a problem for the precast concrete industry, also for other industries like the wood industry that also has issues or had issues with diaphragms, and for the tilt-up buildings. And I mentioned tilt-up buildings. Write a note for those of you who love to do work on tilt-up. Very little research has been done, and it's a huge opportunity to team up with key people in the industry because there is a lot of need to work in tilt-up, particularly in connection, diaphragm transfers, and at that level. Okay, so the rationale for laboratory testing, I'm not going to read these things. I'm just going to skim through for the sake of time. You will have access to this. But when we started this, there was no information on precast diaphragm connectors. We didn't have anything. They were connectors, but we didn't know, are they okay? Are they strong? Are they brittle? So we really needed to classify those connectors. And to classify those connectors, we decided to use the, in those days, NIS, now NHERI, Lehigh facility, because we could do hybrid testing there in control tests. So we tested many of the type of connectors that were used in industry, and we classify them into the formable and also the formable connectors that can be used on the East Coast and can be used here on the West Coast. So that was comprehensive, the amount of work done at Lehigh University. Once we have done all this testing at Lehigh University, we calibrated our group at the University of Arizona, did some detailed model nonlinear finite element model calibration in ANSYS, and robust, because we had connectors that were placed in shear and axial, and the response actually was coupled, so it was not uncoupled. That is independent. The shear response is independent from axial, so they had to be coupled. And then once this was understood, we began to do work. We were working in parallel here at UCSD, looking mainly at the inertia forces that develop in these buildings, not with the same degree of granularity as our peers at Lehigh, but we were able to do thousands of analyses as well. Then once we compile all this information, we came back and said, look, we are ready to do a capstone test. And we built this building, a 3-story building that we call it the parking building, or the PCI building, that was wider than the shaking table then. At the time when we put the proposal to NSF, we did not have the shaking table, and we were going to do little testing, but they were toys. But by having the shaking table available when we were ready to do the testing, we were able to use connections that were built at 1/2 scale with the same response characteristics as those that were full scale. So this is more or less in a nutshell what we were doing. Our work here at UCSD was mainly doing many multi-degree of freedom analysis, where University of Arizona was doing very granular, very detailed finite element analysis that was done based on the calibration of the different components that were done at Lehigh University. So all that end up with the testing, the capstone testing at UCSD. So here you can see some that the precast concrete elements tend to open up discrete gaps in between the units. And for example, if we have welded precast units, that poses a big challenge to ensure that the weld is going to, the field weld is going to be able to absorb the deformation demands. These are the models that were done at Lehigh with at University of Arizona with the support of the testing at Lehigh. And you can see here some of the testing. You can see hybrid testing done on a building. And this way we were able to calibrate many connectors that were available in the industry, as well as new connectors that were highly deformable, because there was the need to develop these connectors as well. This is the testing that we did at UCSD. You can see the yellow blueprint is the width of the shaking table, and the building itself is 3 times as wide. So we put this building on hydrostatic bearings that we actually fabricated them here. And to do a repetitive number of tests, we decided that the best option for us was to put the lateral system given by these structural walls on low damage walls. So they were post-tension and they were well armored at the ends. And we did something like, off the top of my head, like 16 design level earthquakes and 8 MCE level earthquakes with very little need for repairs. At some point, we did cut the energy dissipators and we grouted new energy dissipators in these walls because we thought that the wall of those dissipators had already undergone severe, substantial number of large amplitude strain cycles. This is the width of the shaking table here, and this is the width of the building there. This is the testing. You can see the bottom right, you can see the wall rocking there quite nicely with very little, if any, damage. It was a pleasure to do this test, actually. These are basically the simulation done through the very detailed nonlinear finite element by Professor Fleischmann's group. You can see the test and the prediction extremely well predicted with these tools. So the deliverables for this project were a new seismic design methodology for precast concrete diaphragms. This is work that was funded by the Charles Pankau Foundation. And from there, we extracted design provisions that made it all the way through balloting and voted through ASC 716 and the 2015 NERP provisions. Now let's go into this other project. It's basically, you could see the architecture of the project is very similar. It's the group from Lehigh, the group from University of Arizona, and the group from UCSD working together. The topic again is diaphragms, but here we are not going to solve a problem for the industry. Here we are we're going to be more like dreaming, what can we do after we observing this? So the building is also precast, but we're trying to do are the accelerations in this building coming through some localized energy dissipation devices. A very large project, again, involving many students, faculty from the 3 universities, international collaborators, and then again, structural engineers like David Marr and Joe Maffei. So the concept itself is that we tend to couple the lateral force resisting system, LFRS, with the gravity load resisting system. So they go together. But if we uncouple them, actually we can decouple them in a way that for a wind or so, or low intensity earthquakes, they can work together, but at some point they separate. Yeah, so these are working together. But when we want to do is separate them here, you see? So by separating, decoupling them and making sure that if we separate them too much, basically we're going to reduce accelerations, and the trade-off is that we're going to increase the relative displacements. So it's a point where we have a well-defined domain or design window where we can optimize these type of designs. So this, you can see a prototype structure that has these wall systems, each one equipped with friction dampers or a small mini BRBs. And to provide restoring force, we have some laminated rubber bearings that you see here. They are carbon fiber rubber bearings that provide the restoring force in case that the friction damper wants to get stuck. In the end, if we have very large displacement demands, we're going to have something where the two systems, the lateral system and the gravity system, can touch one another to provide some restoring force. It's a system here, the dampers and the rubber bearings. So though you can see here is the backing restraint brace, right? With the rubber bearings providing the restoring force and ensuring that at the end of the earthquake, we have a minimum residual displacement. So it goes back to the initial position. And this can be done through BRBs or friction devices. In the end, if we're going to exceed the gap between these, we have a receiving bumper, which is a polyurethane bumper, and we don't want to have a huge impact, but something that is more or less controlled. You can see here the testing on the laminated rubber bearings. These are carbon fiber laminated, so you can cast like a bed or a chocolate block of these things and then water cut them. Very easy. You don't have to be concerned about corrosion, anything less, because when you look at isolators or elastomeric bearings, if you're using steel laminates, you need to protect them from corroding. Here are the carbon fiber rubber bearings, the friction devices. This is the testing at Lehigh University by Professor Champras. The different components included the bumper, and here is the bumper heating. This is one of the tests. You can see there, very cool. So again, the topic here is that we have testing on the individual components, a lot of analytical work, model development, and in the end, once we understand the problem, we have a capstone test. This is our capstone test. It was a 4-story building. Again, the topic was that we were going to use low damage post-tension walls. We team up with the precast concrete industry. They provided the walls for this project and the columns that were also precast. It was about a scale 1 in 2.5, half a scale. I think it's actually 1 in 2.5 or so. It was designed to provide direct comparison between the system being proposed and the traditional. So we had ways to log the system in place. So we do initially the testing on the system we want to propose, and then we log the system in place and made it work that the gravity system and the lateral force resisting system are tied together like in a conventional building. And in that way, we're going to increase the accelerations and see greater response. And we use the low damage walls for repeatability. So here is the scheme of this. And one interesting part of this is because we are here not meeting any codes or anything like that. The shaking table was in 1 degree of freedom configuration, translation along the longitudinal axis of the shaking table. We placed the longitudinal wall very eccentric, and by having the wall very eccentric, we were exercising torsion, huge torsion, and by doing that with a single degree of freedom excitation, we could test friction dampers in the longitudinal direction and mini BRBs in the transverse direction. So we basically with the limitations that we had there of single axis excitation, we were able to do 2-axis excitation in the building for the components. So this is the kind of work we did. So you can see the rocking here, post-tension walls, and you can see here it's the friction device is being coupled now between the diaphragm and the lateral system, and we have a gap in between. And in that gap, remember, we have the carbon fiber rubber bearings providing that restoring force. And in the end, we leave a gap with the rubber bearing here for the case of impact. A lot of instrumentation we had in this building, and this is something I think we had of the order of 200 to 300 sensors to capture accelerations, displacement, relative displacements. We also have GPS devices coupled with accelerometers to measure lateral displacements of the building and the torsion. You can see one here. And here is one of the responses of the friction device. You can see the building twisting on the right. I think all these videos, this presentation, I will make it available so you all can take a look again at this. And this is a full response of the friction damper, and you can see the bumper there. You see it hitting the bumper big time. How am I doing for time? I think I'm pretty much about to complete, so it will be. Here is the system on the left and the system on the right, the traditional. You can see the differences. I don't think you need to put sensors to basically quantify that the system being proposed as a reduced response compared to the traditional system. And here it's some comparison of the responses. Let's say, for example, here at the end, you can see phase 1, which is the IFAS, very reduced response compared to phase 2, where we lock the system. So you can see very, very differences in responses. I think with that, I just want to acknowledge Professor Fleischman, who led these two projects. It's been a pleasure to work with him, and with my colleagues at Lehigh University, Professor Richard Sauls. It's been a pleasure to work with him as well. And I think I'm open for questions. So thank you very much.
Thank you very much, Jose. Are there any questions for Professor Restrepo?
See any questions in the chat or in the Q&A. If you have any questions you'd like to speak up, please raise your hand and we can unmute you and you can ask your question. Otherwise, please put it in the Q&A or the chat.
Please don't be shy. Once again, there are no stupid questions. If you think you have not understood something that he mentioned.
Yeah, particularly with the way you work as a team, maybe the technical side is very specific to these projects, but questions about the implementation or things that are more global that you think will make your proposal more sellable to NSF. So I think this is where we can perhaps comment a little bit more. There is one here. Hi, Enrique. So in my opinion, what will be the most challenging part, common part of all projects? This is adrenaline driven. The most challenging part is safety, making sure that at the end we walk out with a project that has been successful, we've taken it to the limit, and we have taken safety seriously. In my opinion, that we don't, that we are able to do the research within the safety constraints that we have, that should be very, very important. The day as a community that we have a collapse on one building or damage. Some of these buildings have been designed for collapse. In fact, the PCI building, we collapse it. And the column that you saw at the very beginning, we also collapse it, but in a contained manner. So it was not a catastrophic damaging collapse, but it did collapse. The column, we fractured 66% of the bars, and it was on the way down when we contained it. And the PCI building, we also had a partial collapse at the end, but we had constrain the building from having a complete collapse. So this part of safety, it's something that we all can give you, and happy to give you advice on how to design for this. If you have little experience, I think is one of our duties here is we don't need to be your co-PI, so all what you need to do is reach out to us and ask for comments about safety, and we'll be very happy to comment on that. Thank you, Enrique.
All right.
Yes, maybe let me reinforce what Professor Restrepo just mentioned. Young researchers among you, you may feel intimidated by the use of such a large facility and perform large-scale, full-scale tests. Nowadays, again, it has evolved. A lot of senior faculty members, senior professional engineers are happy to act as advisor without requesting to be a co-PI. I think it's very important to keep this in mind.
Right.
I have a question, Jose. This is Chris Antelevis, University of Utah. How are you?
Very good. Thank you.
Thank you for a great presentation. First of all, my comment is Ευχαριστώ is missing from your last slide, which I will send it to you later in Greek. Maybe that's why it's not on your last slide. But the other question is, okay, great systems on the shake table and great results. How long does it take to implement such great systems in the real life, in the real world?
Yeah, for the precast diaphragm, we started back in 2002 with the idea. We were funded in 2004, begin to work in 2004. We completed this project in 2008, and in about 2013, we begin to work proactively with BSSC to place these recommendations on NERP. And NERP is the mother of all codes and was balloted several times. And in the end, it went to ASC 716. So from the incipient idea to being put in the ASC standard, we have 14 years, right? But let's say that you can cut those to about 10 years. I would say it's a 10-year cycle or so, 10 to 14 years to have these things implemented.
So is there any building that's built like this?
Oh yeah, absolutely.
Okay.
Yeah, all the precast concrete industry is using that on the west, east coast and Midwest as well.
Okay.
Many of them.
Thank you very much. This is very important, of course.
Thank you, Chris.
Any other questions? Doesn't seem.
I would love to hear from assistant professors or so. That's it will be wonderful if you have some question to ask, and I'll be very, very happy. You'll make my day if you ask questions or so.
I think we have maybe let me see if I can stimulate some question. How about Dimitrios Kalyontsis, one of our ex-postdoc? Any question?
They may be on mute, Joel. I know Korosh has to unmute in the attendee mode.
Yeah, I've allowed.
Oh, gotcha.
Permission, yeah.
Got it.
Actually, I'm just enabling everyone at this stage, just to open discussion if there's anything.
Yeah, please feel free to ask question about anything that is in your mind. Any presentation you have seen this morning. I guess everything has been very clear.
I think areas where you can find support are.
Oh, there is one, David, Davide.
Hello. Hello, Professor Restrepo. I'm Davide Gorini, Sapienza University of Rome. And thank you very much for this challenging and fascinating presentation. And I would have just a curiosity regarding the effectiveness of these, in particular of the last anti-seismic solution, because just to have an idea about the order of magnitude of the seismic effectiveness of this solution, because I work on, I currently work on other anti-seismic solutions such as tumor dampers and of different kinds for conventional and non-conventional tumor dampers, and so I would just have an idea about the efficiency of these novel solutions you are proposing. Thank you.
Yes, I think the first one is very straightforward. It's directly applicable to industry, response to industry needs. The other one is kind of a dream to look for this. And as soon as we finish this project, talking to architects or so, we realized that this project can have severe architectural constraints. So it will be more limited. And by the time you look at these solutions, you could think that seismic isolation per se is a simple solution. But it was interesting, and it was interesting from the point of view of science and model development. I don't know the applicability of this other project. That's what I wanted to separate the two projects. One is in direct response to industry needs. The other one is more like a dream on see how can we diminish this, and we'll be competing with many other solutions. I still believe that seismic isolation provides a quick response to many of these needs as well.
Thank you. I see. Thank you very much.
Thank you. We do have one question from Demetrios, and I know Enrique has his hand up as well, but Demetrios doesn't have a microphone, so I figured I'd just read it out. The following question: in an NSF proposal of that magnitude, what percentage of the budget goes to shake table testing?
I would say, let's say that you're going to shoot initially. Let's say you're not going to rely on other sources of funding. Let's say you're going to shoot for $1.4, $1.2 million. I would say easily 50% will go into this. And the main reason is the demolition cost. For example, for a structure like that is a huge item. In California, you can easily spend $100,000 to $150,000, if no more, demolishing one of these buildings. So I wouldn't be surprised 600 or so. It's probably will take you some, and you will be looking for alternative sources of funding as well.
Related to this question, let me also clarify, we didn't mention this morning, but so that it's clear, you know, what does the site pay and what does the researcher pay? So it's pretty simple conceptually. Is if you receive funding, you know, from NSF, so in your budget, let me tell you what the site is paying for. So the site has the responsibility to install your specimen on the shake table platen, very often post-tension it to the shake table platen. The site is responsible to instrument the building, as long as you don't have some unique type of sensors that we do not have here. In this case, we would ask you to bring these sensors, and we will try to accommodate them to the data acquisition system that we have. If not, you may need to bring your own data acquisition system. But with traditional sensors, the one that you have seen in the presentation, so we instrument, of course, under your direction. We assist you in deploying the sensors, and then we run the test. We give you the data, and you are responsible to build the specimen. Usually you have several options for this. You can ask for outside contractors, and we have a long list, like Professor Hutchinson told you, that we can propose to you. But even if you bring the outside contractors, we still need to involve, for example, Alex Sherman, who is the safety officer here, because the outside contractors, they have to interface with the site. If our machines are used, the crane, the boom lift, and other things, only our staff can operate this equipment, and this has to be put in your budget. You know, the number of hours of using this equipment. We have the recharge rate on our design on our website at Design Safe, and then you need also to pay for the demolition, like Professor Restrepo just mentioned. So basically, summary: you pay for the construction of the specimen, the demolition of the specimen, and if you damage sensors during your most critical test, then we ask also for reimbursement or basically buying new sensors. Don't know if there are maybe also questions related to that. So if you don't have a lot of experience and you want to know how many hours of our technicians and how many hours of use of our machines should you budget for, we can have, our team can have discussions with you, or you can also talk to researchers who used our facility in the past.
I could add to the question Jose addressed regarding the percentage of budget going towards the shake table testing. And Jose is absolutely right. The demolition costs can be quite extraneous, but it does depend a little bit. It does depend quite a bit on your specimen. In one specimen case, we had a prefabricated structure which we de-erected, and the specimens were of interest, and they were metal, and so they were recyclable. Parts of them were recyclable. So that was a benefit to reducing the cost. I think the cost of the 6-story cold form steel demolition was on the order of $60,000 or $70,000. But for contrast, a comparable height concrete moment frame building, the BNCS project, the demolition cost was upwards of $350,000. And that was including some recycling of the concrete and excluding non-structural demolition costs. So there's a dichotomy depending upon the specimen, materials and typology, obviously.
Thank you. We have one question in the Q&A. Do you have any fabrication facilities on site?
Rush, maybe you can.
Yeah, sure. We can assist with fabrication depending on what it is that you need made. We do have plenty of tools and equipment that we can use, and we have a small machine shop with your common tools to fabricate components, but it all depends on what it is that you need to fabricate, how large it is, how technical it is, and if we have the capabilities. So I would suggest get in touch with us, our staff. We're more than happy to talk with you and work through what you need. And if it's something we can do in-house, we can. If not, we can suggest or recommend local contractors or machine shops if you need anything machined, who've worked with us well in the past, and we can put you in touch with them. But again, going back to the costs, since the NHERI facility, we don't, NSF doesn't cover the cost of any kind of construction or fabrication. That is something that you should budget for in your proposal. I hope that answers your question.
Yeah, thanks all of you for your responses. Yeah, I mean, I was mainly interested in the percentage of the budget, like how much it would cover from the cost of the total project. I have tried in the past submit a proposal, and I'm also working on probably coming with a new idea on that, but kind of get a little bit on the idea of how what should be accounted in and what is taken care of by the site. But thanks all for your responses.
I think a good example is to have is to use one of the project management tools where you have a timeline and with money embedded into each task, or so time and money, and always be a little bit conservative in the time, because usually things tend to stretch a little bit longer than you expect. So it's not a bad idea to do that exercise and not to be over optimistic or so.
Any other questions?
Yes, we have another question in the Q&A. If we have UCSD colleagues as a co-PI, could UCSD's indirect costs be reduced as we have paid the recharge to the UCSD?
Let me see. So the question is if an outside researcher involves a UCSD faculty as a co-PI, could you repeat again the?
Could UCSD's IDC, the indirect cost, be reduced as we have paid the recharge to UCSD?
It's a good question. We never had to deal with this in the past. I think that for sure, you know, every effort will be made to avoid a double charge. Right, so to pay a double IDC at two different universities. But we would.
This is a very good question, and perhaps you may want to inquire this further and give a written answer later on, Joella, because it's a very important question.
Yeah, but it's tricky because the indirect cost you're paying is for the portion that's paying for the grad student and the personnel costs for that portion of the project. It's not the IDC you're paying for the entire project. So it gets a little tricky. I'm not sure how Tara's past projects and Jose, yours with other sites has worked out that way.
Yeah, I think that you always have your total budget for your UCSD subcontractor collaborative portion, and I think the IDC is blanketly required to be applied.
I have had cases where the demolition is paid by, let's say, PCI directly or somebody from PCI, so it doesn't have to, the money doesn't have to come through UCSD where it's going to have a markup. And let's say the demolition is $100,000. If it comes through UCSD for me to use, it's going to cost $150,000.
And it's direct, yeah.
Give or take, which makes no sense. So the organization pays directly for that, and that saves a lot of money to the project.
But if you've had recharge costs in terms of the staff's time just to oversight that demolition, then that's in your research budget, unless you pull that out in the as a donation portion of it. So you would still have IDC atop any recharge category.
Yeah, but the money, whether I'm going to use the money from the PI institution will come with IDC, and then even if it comes from the PI from NSF directly to me, it comes with IDC, and on top of that, I need to pay for the recharge rate, whatever it is, you know.
Yeah, right.
Yeah, I think that this issue, it's not only a UCSD issue, would be also an issue between you and whoever asked the question, between you and your university, the Office of Contract and Grants. You would imagine that your university would charge indirect cost only on maybe the first so many dollars, you know, of a subcontract, because basically you would need to open an impound account here and migrate money to this account from your budget to pay for the recharge, you know, to pay our technician or the use of the machine. So since this money, you know, is charged indirect cost from UCSD, we would hope that your university would not tax you IDC on this money that you use to pay UCSD. So it's not only a question for one university. We would need to clarify things here, and you would need to clarify things at your university as well. And to reinforce what was said, if you hire a contractor directly from your university, you would save the IDC from UCSD. Right? The 43% right now is a reduced IDC, but it's still high. And the only requirement that UCSD has is that whichever contractor you bring on site has to have a certain insurance, a certain level of insurance. I think $3 or $5 million of insurance. It takes some time to fill this paperwork and to have it accepted.
Okay, thank you very much. I don't see any additional questions.
Hello, Joel. I have one more question, if possible.
Yes.
I mean, the UCSD upgrade, I mean, it has been out there for a while now. And I'm curious if any of the future projects that are being planned to use the table are actually like utilizing the 6 degree of freedom capability, or if there have been projects being submitted that are motivated by this capability. If you know what I mean, like in the sense that if a project is actually like, you know, utilizing this capability to kind of motivate research that, you know, like I'm not talking about a specific project, but in general, if it's happening in proposal submissions.
Well, I mean, we do not know yet what earthquake records the 10-story building will use. I mean, we will exercise all 6 up to a certain degree, you know, to maybe for the 3-story test frame that we will test as the first project. But I cannot answer for the 10-story building. More general, if you go back in the literature, there are quite a number of numerical modeling and simulation papers that show that the rotational degree of freedom could play a significant role in a number of situations, and some reconnaissance effort after earthquakes also have concluded that for certain failure modes to occur, there must have been some rotational component of ground motion and so on. And if you go in the field of ground motion seismology, there is a brand new subfield that has emerged in the last 10 or 15 years, which is, I think it's just called rotational ground motion seismology, because they can measure more and more accurately rotational ground motion components. And you know, I think there is a very good chance that in the future they will play a role all the way to the design code, I think. I don't know if it was your question.
Yeah, I mean, basically, I'm just curious if researchers are actually tend to, you know, be motivated by this capability to actually go beyond the uniaxial testing to look into factors, as you mentioned, that have been like observed analytically to actually test specimens to show that. And if like that is kind of a motivation to develop a proposal in the first place, or is just that someone has a different idea and they're just submitting a proposal. And by the way, we can just utilize this capability to just expand our research results, or is it kind of the main focus that you are actually want to discover what is happening if a structure is experiencing all these like different ground motions, different directions?
Yeah, we will have to wait to know. I mean, I don't know what people are putting in their proposal at this point.
Thanks.
Hey, any other questions or discussions before we adjourn?
Okay, so it looks like there are no more. Maybe I will just quickly say a few things for tomorrow. Let's see here. All right, so like I presented earlier, right, so we're done with the first day. I want to thank all the presenters for their presentation and for you for attending. I hope you received some information that you were looking for. If you cannot attend tomorrow, we have a survey that we would like you to fill that I think my colleague Lelia will say a few words in a minute about. And if you can attend tomorrow, there's some exciting presentation about this modular testbed frame that can be used by researchers, very modular frame, tallwood, the 10-story tallwood project. We have three presenters about it. Dr. Kusatis from the National Science Foundation and Dr. Elena Kalinina from Sandia National Laboratories and Mr. Nicholas Klimishin from the Pacific Northwest National Laboratory, talking about the upcoming testing of nuclear casks and surrogate model for the nuclear fuel. And then Dr. Lotfizadeh about IT resources, cybersecurity and instrumentation data acquisition. So if you can attend tomorrow, you can get also very valuable information on our facility. And maybe Lely, you want to add something about the survey?
Yeah, I mean, we will be sending out a link to the survey towards the end of tomorrow's session, and that we highly encourage you. It gives us feedback on how we can improve the delivery, the type of content and the delivery. Obviously, you know, what about whether, you know, the remote sessions are, how we can improve basically the engagement and everything related to the way we delivered this. So, you know, we'll send this out. I don't know, Kurosh, if you'll email it to them. We'll maybe post it in the chat for those that are there tomorrow, but we'll also email you the link. And again, it'd be really beneficial if you guys could participate. And it's anonymous. You're welcome to add your email address at the end if you would like us to contact you directly, but otherwise it's anonymous.
Very good. So I think we are ready to adjourn unless there is another question. Kurosh, any? No?
No other questions at this point.
Okay, very good. So again, thank you very much for attending. Have a good afternoon, good evening, or good night for some of you. Thank you for having stayed late. If for some of you, it may be probably close to midnight now. So we will see you tomorrow.
Bye-bye, everyone.
Thank you very much.
Thank you.